Great. All right. So hopefully this inconvenience is only temporary till the IT comes back. Okay, without further ado, welcome to the tutorial for ML systems for large models and federated learning. So this is a two-part tutorial with three presenters. There is myself here in person. I'm Chirong Ho from the Mohammed bin Zayed University of Artificial Intelligence. That's a recently started AI university in the United Arab Emirates. And joining me online are Hoi Wang from Carnegie Mellon University, as well as Samuel Horvath, who is also a faculty like me from MBZ UAI. And we roughly divide the tutorial into three 1-hour blocks with a 15-minute break in between. So you will see us switch presenters as we go. Okay, so on to the beginning of the tutorial. So we're going to start first with the large ML models part and then segue into the federated learning, although you will see there are interconnected topics between the two parts of the tutorial. And the motivation for us here is that with the growing scale of AI and ML, some facts and numbers here. By the way, I've switched to the first slide of the presentation. We've seen a accelerating trend in the size of models, which is you can see in the graph here. It used to be that model parameter counts in all of AI. If we look at just the largest models here, tended to about double every year, but most recently they've accelerated to an astounding 40 times increase per year, particularly with the advent of the transformer architecture as put in use in natural language processing, but also making its way into computer vision topics. So with this growing model complexity also came an accompaniment with growing data size. For example, many of the large language models these days are trained on corpora of over 1 trillion tokens. And of course, likewise, dataset sizes in vision as well continue to increase every year. So with these compounding factors, the compute cost to train state-of-the-art models has on average been about 2.4 times every 3.4 months. And then we're going to run into a set of challenges that I'm sure some of you are familiar with, but I'll state them, right? First of all is the computation challenge, the fact that it requires just very much hardware. But there's also additional challenges that even if you have the computation, you have a memory issue in that some of these models don't fit on a single device. You have a communication issue because you have to send basically the model updates between different devices. And as we will soon see, the amount of bandwidth that you have to do so outside of a single box is actually fairly limited. And then there's also an issue of user expertise. Now that bar to entry that's based on user expertise has come down on the software side, but there's still issues of perils and pitfalls such as selection of batch size, learning rate, or as we will see in the tutorial, we will get into advanced strategies for decomposing a model into parallel components called model and pipeline parallelism. There is an element of the user needing to choose how to slice and dice that model. And that slicing actually takes a little bit of expertise, but that's hopefully what this tutorial will give everyone an introduction to. So turning over to the next slide. Now, let's talk a little bit about the challenges in a bit more detail, right? Compute challenge is really one of how many floating point operations can we push to the model per second. And the rough number that everyone probably has realized by now is that on a single machine, even if that machine costs $200,000 and there's 8 GPUs in it, it will take decades to train a, let's say, 175 billion parameter model or 1 trillion tokens. The numbers are there on the slide. Basically, we have 10 to the 15 floating point operations per second for one of these so-called DGX grade machines. But the models require something like 10 to the 24 computation. So that's something like 10 to the 9 seconds, which is 15 years. But what's less obvious other than the raw compute challenge is that how do we make sure that we choose the algorithms and software to do this training in an efficient and correct manner? And sometimes there are trade-offs that may not be obvious if you're new to the practice of this. We also need to think about the user effort issue. Is it worth investing all of that effort into making for example, a really specialized or customized parallel strategy? And what's the trade-off with time and cost savings? And of course, in this tutorial, we're also going to talk about federated AI, which exposes a whole new set of concerns, but we'll leave that until we get to the federated AI part of the tutorial. So next slide. Memory challenge. The primer here that you all need to know is that when you think about how large models are trained on GPUs, the parameters, the amount of memory that's used to store the parameters is actually only a fraction of the memory that needs to be consumed, right? Because what happens is that with your batch size, the intermediate states and activations will grow with that batch size. The surprising fact here is that even with a batch size of 1 or micro batch size of 1 per GPU, you still find that the activations, even for a transformer model, are actually bigger than the parameters. In computer vision, for computer vision models, convolutional architectures, it's more common to use larger batch size in the dozens. And those batch sizes, then the ratio of basically intermediate activations created by the batches moving through the architecture, that ratio becomes something like 10 to 1 or even 20 to 1. So depending on whether you are doing a natural language processing or language model or computer vision model, that ratio of activations to parameters is anywhere from 5 to 1 to 20 to 1. And if you think about what this means, you have a 175 billion parameter model. You're trying to store that as 4-bit floating point. That's 700 gigabytes of memory. Already you have problems fitting that on any GPU today. And then now you have that batch intermediate activation issue to contend with as well. So you can see that you can't fit the model and its associated states. And there's also other things, like if you use an Adam optimizer or more any optimizer that's more sophisticated than baseline SGD, you will also have to store things like higher order moments or estimates of those moments. That also consumes memory. And so all of these things add together to mean that some sophistication must be built into the software or strategies in order to get these models to even fit on the GPUs for training. Okay. Now, let's talk a little bit about communication challenge. Again, this is all primer to make sure we understand the rough order of magnitude that we're dealing with here. So in this communication challenge, right, if we think about how much, again, the memory required to store any model that's over 100 billion parameters is in the hundreds of gigabytes. Ergo, the gradients for such a model are also in total hundreds of gigabytes. And you want to send this hopefully, several times a minute, if not several times per second, if you have a really large cluster. Now, what's the bandwidth actually between GPUs in the same machine or even GPUs in a different machine? So for a high performance machine, DGX class hardware, we're talking about 600 gigabytes per second between any pair of GPUs. This is for the A100 generation of GPUs. H100s might be a little bit better than this, but the instant you go between two machines, in the best case scenario, you will maybe have a hardware setup where every GPU is pinned to one InfiniBand port. InfiniBand being basically NVIDIA's preferred adapter for their DGX class machines. That InfiniBand adapter has 200 gigabits per second, which is 25 gigabytes per second. You can see that's more than 20 times less than point-to-point transfers in a single machine. As we will see, this has very strong implications for the way parallel strategies are designed when you have either one machine or multiple machines. There are specific ways that they have to be designed to overcome this 20x gap in bandwidth. And when we get to federated learning, the bandwidth is going to be even smaller and a whole new set of challenges will arise. Next slide. So, and by the way, for people that just came in, I apologize. There is a technical issue with ports and mismatch with the machine. What we are doing right now is that we're encouraging people to either log into the Zoom so they can follow along with the share screen, or on the project page, I have just posted the slides. So the slides are available if you wish to follow along that way. The IT people have promised to come back. They have not yet come back, but hopefully they will and fix this problem. Okay, back to the tutorial proper. And let me make sure I do a time check. Okay, so, and the last challenge is the one of getting familiar with the software that's required to run these models at scale. In the past decade, there's been an explosion of what we call ML systems research, where people have investigated the various ways to put together all sorts of different innovations in order to make the research work at scale. The only problem is that now there's so many of them that it can be hard for a newcomer to decode. So we're going to have some recommendations for that, but it's also a matter of understanding, not just recommending the software, but actually understanding what the software does so that you know when it's suitable to apply and when you might be better off picking a different piece of software. Okay. So that's all for the preliminaries. And now on to the next slide, we are going to formally begin the first part of the tutorial, which is the background for parallel, distributed, and federated learning. So next slide. So we're dealing at a little bit of math here, but I promise there won't be too much math in this tutorial. We are basically dealing with machine learning or artificial intelligence programs that take the form of a maximization or minimization of a loss function over data X and model parameters, which we denote A throughout the first part of this tutorial. Next slide. So and these optimization problems essentially give rise to a, when coupled with an optimization algorithm, such as stochastic gradient descent, it gives rise to an iterative convergent update function, which is in the bottom of the slide. We're going to use this notation throughout, where the parameters at the next iteration T are the result of first applying a update function, for example, computing stochastic gradients, followed by some kind of aggregation function, which manipulates those gradients by summing them together, or if you're using momentum, SGD or Adam, more complicated things happen in that F function. But this is a general form we're going to deal with just so that we're on the same mathematical page throughout. Next slide. So, and then this equation essentially shows up in a for loop, where the loop is over different iterations or epochs of your training run. And then there will be code that does something beforehand and after, but this core loop always exists somewhere in the middle. Okay, next slide. And now, when we think about parallelization for these machine learning or artificial intelligence programs, the fact that they are optimization programs, iterative convergent, meaning that they iterate until a stopping criterion, instead of having a one-step closed form, means that we have several properties that have been historically exploited throughout the history of trying to get us to train larger and larger models. The first property is error tolerance. The fact that we are robust to noise, in fact, by definition, SGD is a noisy algorithm. So the fact that these algorithms are robust to noise, being a hill climbing algorithm, means that this can be exploited to do things like manipulate the batch size or manipulate learning rate, which is something that people do whether or not they're going distributed. But as we will see, this has becomes more and more important as you go distributed due to a phenomenon where the minimum batch size for data parallelism is equal to the number of GPUs. So as you get more and more GPUs, you're forced to increase the batch size. What does that mean for you? Can we avoid increasing the batch size? And there's even been techniques where, like such as quantization, such as sparsification, where in order to get even more speed or even more memory reduction, we are making those gradients noisier and noisier. So error tolerance is the most important property. Another property that's historically been exploited is the uneven convergence of parameters, in which different parts of the model actually converge at different rates. People that are very familiar with fine-tuning parts of the models have probably noticed this, but this can actually be exploited by certain methods. Structure in parameters, this is pretty much obvious in the deep learning era. Tuning sensitivity, where we have to manipulate certain sets of hyperparameters, most notably the learning rate, but there's also, depending on the model, there may be additional hyperparameters, and this again is a characteristic that affects how many iterations it takes to converge. And finally, the fact that in modern ML software design, everything is composed out of essentially building blocks in PyTorch or TensorFlow or JAX, depending which language you use, you have the operator primitives, right? And then if you use supporting libraries, you may get entire layers or blocks of layers with inputs and outputs, and that's actually how we interface with that. But it has implications not just for the user. It's convenient for us to do that. It has implications for the software systems, because if the software system knows that the user is always going to specify their model as these blocks, people optimize around that. As an example, right, transformer models are essentially, for the most part, this transformer layer that's repeated like 96 times or more in larger models. because it's exactly the same layer every time, which is quite different from a convolutional net in which the layers will shrink as or expand in the case of a UNet, right? But coming back to the transformer example, the fact that it's the same block every time means that people have designed model parallelism strategies around that transformer block alone with the expectation of being able to tile it over many machines. So this is how compositional assembly actually affects the thinking and the way people parallelize machine learning programs. Okay, now just a quick check. People online, so far so good. Everything clear? Can everything be heard? Hongi or Sam, can you let me know if things are good on the online end?
Yeah, we can hear you well, Jerome.
Yeah, perfect. All right, onward. So onwards with the tutorial. So next slide. Okay, now we're going to talk about some basics of parallelism, and I'm going to approach this from both a mathematical level and then flip over and look at it from the system or like operator by operator level. So at the mathematical level, and this is the way most people in machine learning think about parallelism, we have three types of parallelism called data parallelism, in which models are replicated across different GPU devices or different computing devices, and data is partitioned across them into from mini batch, stochastic mini batch SGD, partition that into micro batches. For example, model parallelism is a type of parallelism in which the responsibility for updating different parameters is partitioned across the computing devices. And then in pipeline parallelism, it's a type of assembly line parallelism where workers line up essentially to receive work, and work passes from one worker to the next one, such that what happens is that every worker is actually working on a different batch of data at any given point in time, but they're updating and computing different parts of the model. So it's related to model parallelism, but the difference is that the workers are actually operating on different pieces of data, just like in a car assembly line, everyone at different parts of the assembly line is actually working on a different physical car. Okay, so mathematically, we can express these forms of parallelism as, next slide, data parallelism is basically, if we take the iterative convergent equation, A equals F of delta, that delta is basically split into a summation over subsets of data XP. This is the simplest and easiest form of parallelism to understand, and that's in particular because everyone in this room presumably knows data SGD and the fact that it's a mini batch algorithm, and then you can chop that mini batch up any way you want. So now let's go something a bit more complicated. Next slide, model parallelism. The iterative convergent form of model parallelism is again A of t equals F of something with delta. What that something is that now delta is not a simple summation, but a set of deltas that are all going to be taken as a tuple input into F, right? Basically, every delta intuitively corresponds to whatever part of the model a particular worker has been assigned to compute, still indexed from P equals 1 to capital P, and then every worker here has a disjoint set of parameters. So in fact, classical example, since this is a computer vision conference, probably everyone knows that AlexNet, when it was first released so many 11 years ago, 2012, right, was actually implemented in a model parallel way because they couldn't fit the model on a GPU, a consumer GPU at that time. So they actually cut the model down vertically, sliced it down the layers, and assigned, one GPU to compute the left half of the model, the other GPU to the right half of the model. So that's a very classic example of model parallelism in action. But every GPU was processing the same batch of data. And that's different from, next slide. By the way, for people who came in, I apologize. There has been a technical mishap with the connectors. What we are doing is that we're encouraging everyone to connect to the Zoom on the virtual site to follow along their devices. The slides are also available on the project page, accessed from the virtual site. So you can follow along by looking at the slides, or you can follow along by joining the Zoom. Again, we apologize. IT was supposed to come in a while ago and they have not. Okay, back to the tutorial. So I'm now on the slide with pipeline parallelism. So in pipeline parallelism, the iterative convergent form of this, you can see it's an A of F and a bunch of composed or nested delta. So every delta takes in some input and gives its output to the next delta in the sequence, right? And then this composition of partial update functions and results in pipeline parallelism, But what it hides here is that at any temporal slice in time, every delta is actually processing a different macro batch of data. So this shouldn't be interpreted as just all happening at this once. It's not a functional program. This is just a crude way to represent the imperative way in which this program is executed as an assembly line. All right, so next slide. And then now, as I promised, we're going to flip over from the high-level mathematical view down to the actual bits and pieces view of how the actual machine learning software actually does parallelism. So what happens in a what we call modern machine learning software are what can be called automatic differentiation systems. For example, the accelerated linear algebra or XLA backend that underpins Google's TensorFlow and JAX is an automatic differentiation system. PyTorch, which is both the front-end programming interface as well as its auto differentiation system, is a single system that's also essentially an auto-diff system. Now, these automatic differentiation systems, when they are combined with parallelization techniques, and this sometimes has to be done by importing other software, DeepSpeed, Megatron, names you may be familiar with, right? When you import other software into PyTorch or TensorFlow, these pieces of software take what is known as the compute graph. The compute graph is a representation of your machine learning program, which you've written in your favorite language, and that's created as a either implicit or explicit graph where nodes are matrices or tensors, which can be inputs, there can be intermediate values, there can be outputs. And another set of nodes are the, so one set of nodes is the intermediate values, tensors, matrices, and the other set of nodes are the compute operations, such as in the example below, convolutional operators, rectified linear units, additions, matrix multiplications. Each of these is represented as a graph, and the semantics of the graph is that for each of the mathematical operators, they will take in one or more matrix or tensor inputs and output a tensor. Okay, so what happens in this inter-operator? So there's two levels of parallelism that happen at the systems level. One is inter-operator parallelism, in which this graph is partitioned and each part is shipped off to a different compute device. In the example below, you see a stage 1, stage 2, stage 3, and stage 4 in a forward pass of a very simple looking part of a neural network. And you can think of each stage as going to a different GPU. And when each GPU computes the operations on that stage, it's going to pass the, I'm sorry, are you checking? Yes, we have a technical issue where my laptop has USB-C and the, right, and we need it for both the microphone and the HDMI. Yes, because this thing has a HDMI and my laptop only has USB-C ports, unfortunately.
Okay, I'll try to find it for you.
Okay, no problem. Thank you. All right. So, back, where was I? So think of every one of these stages as existing on some GPU. And when the GPU is done with a particular micro batch of data that goes through and they come in as X, they come out as the output of that addition operator. Those outputs then go into the next stage and so on and so forth. This is called in the systems lingo, it is called inter-operator. Oh, I really appreciate that. Thank you. Let's at least get the projector working. Okay. I should have asked the audience if well, thank you. You just saved us. So let me take a second to at least get one of the systems working, the most important one. Okay, great. Well, this saves everyone from staring at their device. Thank you so much. Okay, we saved the 5/6 of the tutorial then. Only 30 minutes in and we've got a solution. All right. So basically this inter-operator parallelism is actually how pipeline parallelism is implemented in a automatic differentiation system, because you can associate each of these stages with one of the deltas that I showed, the previous pipeline parallelism slide. You have each of the deltas. They actually correspond directly to these stages in inter-operator parallelism. So it's a simple matter of cutting the graph up. Well, I say simple, but it turns out that there are a lot of considerations, like you want for example, the matrices or tensors that flow between stages to be as small as possible. And you will also see that there's a load balancing issue. Currently, what's the problem with this partitioning? You've got one stage with a single operator and other stages with many operators. This is not going to be load balanced, and you will have the speed of a parallel system is the speed of your slowest worker in the system. So we will talk more about this, but this is the connection between how the ML system actually does the parallelism and how we as people who operate on the level of loss functions think about parallelism. The other implementation detail that you need to know is called intra-operator parallelism. The previous slide was inter-operator parallelism, which is about dividing up the graph, but intra-operator parallelism takes a single node in the graph and chops it up further. So it basically occurs at the level of mathematical operations, and you take a single math operation, say a matrix multiplication or convolution, you break that up into sub-matrices or terms that will either need to be assigned to different parallel device or need to be added or reduced together in some fashion, right? And then based on how you partition the output, you partition the inputs accordingly so that every GPU device has all the necessary inputs to compute its fragment of the output. Simple example, matrix multiplication. If I'm taking this output C and chopping it 4 ways, and let's look at the first upper left purple block, right? What you need are the first 2 rows of the A matrix and the first 2 columns of the B matrix. You don't actually need anything else, which is important for saving communication. Because if you had to send all of A and all of B to every single parallel device, that would be unnecessarily expensive. Convolutional example, if you're convolving basically this weight matrix A with the data matrix X, then say a single cell of the output here would correspond to taking all of the weight matrix A and doing a convolution operator with this pale red segment over there. So these are just 2 simple examples of how intra-operator parallelism can look. And what happens in systems like XLA or PyTorch is that for every mathematical operator that could exist in your graph, you'll need to implement the according intra-operator parallelism mechanism. Hello, so a kind audience member has lent me an adapter. We still need a USB-C to deal with this. Oh, actually, this thing seems to have a plug. Oh, I hope this doesn't. Yes, if you can get one, I feel very bad for borrowing an audience member's adapter. Okay, all right. Yes. Yes. Okay. Sorry, that goes that to him. Yes. Well. Yes. I'll. Who do I return this to after the tutorial is done? Just outside. Okay. I appreciate it. This is just for until the tutorial's over, which will be in 2 hours or so. I appreciate it. Okay. All right. Hey. All right. Okay, let me just stop my share to change my device. Okay. Let's see, microphone. Speaking. Okay. Just a quick mic test here. People online, can you Sam and Hongyi, is the microphone still good?
Yes.
Okay, that's wonderful. And let me resume the share. Okay. With that. All right. So back to where we were. Intra-operator parallelism.
Sorry, Hongyi. Now we can actually see. Sorry, Chunks. So now we can actually see your second screen. So
you're seeing the wrong
I can
screen.
see the presentation mode.
Yeah,
Okay,
we're seeing
let
the
me
presenters
fix
mode.
that. Let me make sure that PowerPoint is doing the correct thing. Okay, folks online, which screen are you seeing now?
Well, still
the
the
presenter mode.
presenter's mode, yeah.
Okay, that's truly unfortunate. Let me make sure that Zoom is picking up the right screen. I'm going to, let's try this.
I think you first want to share and then like you first want to start the presentation and then share.
All right,
That-
I see
that
what
should
you're
do
saying.
the job. Yeah.
Let's try this. Are you seeing the correct one now? Do you see the correct screen now, or still the
I
wrong one?
only see that you started sharing. Now I actually cannot see anything. It only says to me like CVPR 2023
Okay,
tutorial has started
try
screen
that
sharing.
again. Yes, so start sharing, and then we're going to share the correct screen here. Let's see, let's try this one. What do you see now?
Yeah, now it works.
Okay, so that glitch is over. All right, so intra-operator parallelism, what you need to know is that if inter-operator parallelism is how the system implements pipeline parallelism, intra-operator is how the system expresses data and model parallelism, right? So that's the connection between the mathematical form and the implementation. But one thing so basically, if you partition data or activation, layer activation matrices by sample dimension in the incoming tensors, that's data parallelism. If you partition the parameter matrices in a non-overlapping manner, that's model parallelism. However, intra-operator parallelism can actually express forms of parallelism that are neither data nor model parallelism. So there's other interesting types of parallelism where you can do a reduction. Let's say you have two matrices, and then you partition in such a way that multiple GPUs compute the full matrix, the full output matrix, but we need to add these output matrices together to get the actual, say, activation or result. This type of parallelism is actually neither data nor model. So bear in mind that intra-operator parallelism is a more expressive space than either data or model. Okay. All right, and it's not something that we can see from the mathematical level because the mathematics of the iterative conversion equation actually hide what we call the imperative operation of the algorithm. So that's why there's a gap between the two. Now, let's dive a little bit more into intra-operator parallelism to help everyone understand how this actually works. So take a very simple perceptron network with two hidden layers, right? You've got a batch of data called B coming in, and you've got, let's look at the weight matrices for the first two layers. Let's ignore the output layer for now. Let's have these weight matrices be dimension D by K1 and then K1 by K2. Okay, and then now what happens if let's say we're thinking AlexNet model parallelism style. We're going to slice that model right perpendicularly through its layers, such that we're going to have the neurons at the top half be computed by one GPU, and the activations of neurons on the bottom half be computed by the second GPU, right? So the boxes here denote who computes which neurons in the perceptron. Okay, then what this corresponds to, that if you make GPU 1 compute the first three neurons of layer 1, then that GPU needs to take the first three columns of the first weight matrix W1. Likewise, GPU2 needs to take as input the second three columns of W2. So what happens is that by partitioning the neurons in a disjoint way, we are made to column partition the W1 matrix, right? Some columns to device 1, some columns to device 2. Okay, and similarly, we did the same thing on the second hidden layer. So again, we're column partitioning the weight matrix W2. So summary side here, parameter matrices, you column partition both of them. And by the way, because they are column partitioned in the forward pass, during the backward pass, they are also column partitioned. And therefore, each GPU updates the elements of the matrix corresponding to its partitioning. That's why this is also called model parallelism. What you just saw, the column partitioning of both matrices, also results in model parallelism when the backward pass happens. Okay, but there's a problem with this naive partitioning, and I'm going to expose that a little bit. So if we take a look at the actual mathematics and communication of this column partitioning, what you will see is that we've column partitioned W1. So let's call the two left submatrices C and E. That's to GPU1. The two right submatrices D and F goes to GPU2. We're going to give the entire input to the layer to both GPUs because they need it, right? And let's call that submatrices X and B from A and B from the data matrix X. Then we're going to call what happens is that we take X, this row X, multiplied by the columns in this left half of W1 to get this triangle, which turns out to be the first half of the neurons in the output layer, in the hidden layer. And then same for GP2, it's going to compute the circle. What happens on the next layer? So W2, if you look at W2, again, it's the same setup. Left half of the columns goes to GPU1, right half of the columns of W2 goes to GPU2. Both GPUs need the full input from the hidden layer. But earlier, we computed only the left half of the hidden layer from GPU1, the right half of GPU2. What does this mean? It means the GPUs actually have to communicate with each other. One of them GPU1 has to send the triangle to GPU2, and GPU2 has to send the circle to GPU1 so that they may process the second hidden layer correctly. Let's consider a different model parallelism strategy where instead of column partitioning the second hidden layer, we're going to row partition it and see what the implications are. Okay, so column partition, first matrix, first layer, so it's the same as the previous slide, but the second layer is going to be row partition. We're going to, and this, as you'll see, does not correspond cleanly to dividing the neurons up. It's going to be something else, as we'll show in a little bit. Okay, now what happens in this arrangement? In this arrangement, layer 1, the output's the same. There's a triangle and a circle. What happens in layer 2? We've row partitioned W matrix. So how does the computation proceed? It's going to take the triangle on GPU1 and then basically multiply it with this, the first half of the rows, G and H, in order to produce this, this vector here, which is the length of all the neurons. Similarly, GPU2 on the bottom half is going to take the red circle. It's going to multiply it with I and J, that's the bottom rows of W2, and it's going to get this full length vector. And then they have to add up these vectors together. So this ACG plus BG gets added to ADI plus BFI, and then this other part, same thing happens. And that's how it creates the hidden output of the second layer. So what has happened here is that this output of the first layer, this triangle on GPU1, did not need to be communicated to GPU2. Likewise, the circle did not need to go to GPU1. So what I've just shown here is a very common technique in large-scale model parallelism, where you alternate between row and column partitioning, which cuts down the communication in half. Why only half? It's because at the end of this second row partition matrix, you have to add up these two vectors, reduce them together to get back the output. And then you need to, well, they're already reduced together on both devices, so you don't need to send them again. But essentially, you're cutting out half the communication operations by alternating this row and column partitioning in a simple feed-forward network. Okay, so that's so this example was meant to show you all the subtleties that occur when you perform model or data parallelism in a neural network. How you actually partition the outputs and inputs can affect dramatically how much communication needs to be done across the entire system. Okay, all right. So that's a little bit of a dive into why intra-operator parallelism is actually a fine art by itself, and why users need to think about such things. Okay, we're going to segue a little bit to give a little bit of background on parallel hardware environments, just so that we're all on the same page when talking about how these parallelisms are actually implemented on hardware. So there's three types of hardware environments that you need to know. Multi-threading, which is parallelism within a single device, which includes parallelism in GPU cores or CPU cores. Now, there's also a type of parallelism between multiple devices that we say that they can share logical memory. This happens between multiple CPUs attached to the same motherboard because they can actually access each other's memory. Note that GPUs, if you plug multiple GPUs into one motherboard, they cannot access each other's memory directly. They have to explicitly send and receive messages to each other. So when we say multi-threading, GPU multi-threading only ever occurs within a single GPU card. CPU multi-threading can occur within all the cores on a single CPU, but it can also occur between cores on different CPU sockets. And that's because CPUs share a single memory space. Okay, we have then multi-device parallelism covers the case where multiple GPUs are socketed into the same motherboard, and they do not share a single memory space, but they communicate with each other using the high-speed NVLink connector in the case of NVIDIA hardware. And then there is multi-node parallelism, or what we call distributed parallelism, where we have multiple machines, each with one or more CPUs or GPUs, and then the parallelism has to be over the network. And then we start triggering the slow communication between multiple devices. Again, they do not share logical memory. So it's important to distinguish that there's actually two types of multi-threading. There's multi-device parallelism, which is unique to GPUs socketed into a single motherboard. And then there's multi-node parallelism, which is a more wider scale form of multi-device parallelism. Okay, I'm going to go through this really quickly, but basically a CPU is basically socketed into a motherboard. It has multiple cores. Each core can run a thread. They all connect. The CPU is connected to some set of memory channels, right? And this is just what we when you parallelize in an operating system, you run what is called a process on the operating system. A process can have multiple threads running on it, and the operating system assigns those threads through the scheduler to different CPU cores. So this is, and then what happens when you have multiple sockets? Then each of these CPUs has some communication bus between them, and this is what allows, say, the left CPU to access the memory modules on the right that are attached to the right CPU. But actually, every one of the memory channels is associated with a particular CPU socket, and a communication bus allows all the CPUs to talk to each other, or, well, not so much talk to each other as we just skip over the CPU and go straight to the memory. So this is how 2-socket, 4-socket servers are architected. Why am I mentioning this? Although most of us don't think of CPUs right now, with the trend of, especially foundation model inference becoming quite the thing, right? We may start to see a division between training hardware and inference hardware. And there's a lot of research going on how to do inference effectively on multi-core CPU-like devices. So that's why this is good to keep in mind. GPU multi-threading is quite a different beast in the sense that GPU threads are not scheduled by the operating system like Linux. They're scheduled by the drivers, which the NVIDIA drivers, for example, are essentially a miniature operating system by themselves. They take in compute expressed in CUDA or NVIDIA or AMD's OpenCL, and then translate that into threads, thread code that runs on the different cores inside a GPU, right? They have a different architecture in that the cores, what we think of as cores, when NVIDIA says they have X shaders or X cores, right? They really group them into these streaming multiprocessor units. So many of their cores combine into one streaming multiprocessor, and each of these things has its own set of L2 and L1 memory, various cache memory. Sorry, they have its own set of L1 memory. Multiple streaming multiprocessors will share an L2 cache, and then that's connected to the GPU memory. So this memory architecture is a little different from CPUs. And for the purposes of this tutorial, you don't need to know what a cache is, other than it's a layer of memory that sits in between the GPUs, 40 gigabyte or 80 gigabyte memory, and then the streaming multiprocessors that actually have to do all the hard work. Okay, so most of this is invisible to us as practitioners because the lowest we will ever go is writing CUDA code. In fact, we can't go lower than that because that's all proprietary NVIDIA secret sauce. So, but it's important to know that they are architecturally different from CPUs, right? And GPU multi-device, multiple GPUs plugged in the motherboard. You have a GPU to GPU communication bus, such as NVLink. You also have a slower CPU to GPU communication bus, PCI Express. Okay, so I've shaded the lines in different thickness because the speed from communicating from GPU to CPU is slow, but communicating from GPU to GPU is fast. What that means is that you only ever want to load the initial model weights and data in the micro batch once from CPU memory to GPU. And then after that, when the GPUs need to exchange things like gradient updates, they're not going to talk to the CPU or go through the CPU. They're actually going to talk directly to each other. And this is how the architecture allows you to, at the start of iteration, you load everything to memory, into GPU memory, and then everyone exchanges gradients over NVLink, which is much faster than going through the CPU. Okay, distributed local area network multi-node is what happens when you take multiple boxes, each of a motherboard and multiple CPUs or GPUs plugged in. And then again, you see a similar architecture where there's a fast high bandwidth connection, usually InfiniBand, and GPUs, the protocol by which two NVIDIA GPUs talk to each other over NVLink and InfiniBand are actually pretty similar. It's all done by the NVIDIA drivers. So the host operating system like Linux doesn't see any of that. So when you tell, when for example, you call, say, NVIDIA's collective communication library and do an all reduced function, you just call it. But under the hood, it's actually deciding, okay, if all the GPUs are on the same machine, I'm going to communicate it this way. And if the GPUs are sitting on different machines, I'm going to communicate it a different way. And that's all hidden from you. But if you read NVIDIA technical blogs, you'll learn things like they may use a ring all reduce if it's like less than 16 devices, or if you have more than 16 devices, which is obviously spread over more than one machine, they'll call something called a double binary tree or reduce. I'm only saying this to let you know that there's a lot of sophistication that goes under the hood of a CUDA or NCCL call. And what you need to know is that the GPUs talk to each other over the InfiniBand link. The CPUs have nothing to do with it. What the CPUs use to talk to each other is some secondary connection, usually 10 gigabit Ethernet, right? So this is the architecture of a modern, say, DGX style machine. Okay, and of course, because we're going to have a federated learning part in the second half of this tutorial, we need to mention a distributed wide area network, which is to say internet level connection. And in this case, we no longer have the fortune to have homogeneous machines with extremely expensive hardware. We basically get whatever hardware exists in the different sites. And then you're going to see high communication latency. It's going to be very heterogeneous and uneven. You're going to have low bandwidth and it's going to be unreliable. You're going to have messages drop, maybe not in the medical setting where you have maybe 10 participants, but certainly in the Google style federated learning setting where you have 1 million smartphones, you're not going to get messages from all of them. So what I'm trying to say here is that federated learning is a completely is a parallel but distinct set of concerns from distributed training, and my collaborators Hongyi and Samuel will talk about it when we get to that part of the tutorial. Okay, so all right. Okay, so on to onward to our session. So in talking about distributed parallel machine learning, we also need to talk about how to measure the performance of a program. Now, I'm sure everyone is familiar with domain-specific metrics. In machine learning, we have F1 scores and validation accuracies. In computer vision, we have IOU. In NLP, we have the blue scores and other types of scores. Just as these domains have different metrics, in machine learning, we're also going to have our own set of metrics. In machine learning parallelism, we also have our own set of metrics. We care about 3 in particular. Throughput, which is the amount of data that gets processed per second going through those GPUs. Statistical efficiency, or more accurately, empirical statistical efficiency, which is the amount of convergence progress or change in loss function or objective per iteration, and something called goodput. This is important. It's the product of throughput and stat efficiency. Okay, so throughput, it's affected, and we'll get to what goodput is in a bit, but throughput is basically affected by the speed of your hardware, what generation of GPUs you're using, how many GPUs you've thrown at the problem. It's also affected by the size or structure of the model, the training batch size, and your communication architecture. Do you have NVLink? Do you not have NVLink? Do you have InfiniBand? Do you not have an InfiniBand? Stat efficiency is affected by the mathematics predominantly, right? It's affected by your batch size and learning rate, most significantly. It's also affected by more advanced parallelism techniques that make use of stillness or consistency models. You tend to see this more in like high-speed CPU inference rather than GPUs. And then you also, if you're applying things like quantization, sparsification, dropout, data sampling, it's also going to affect your stat efficiency. So this thing intersects with the systems, between the systems and the machine learning program and algorithm. Okay, we define throughput very simply as the number of times the aggregation function f. You execute that once per iteration. So number of times f has been computed, which is the number of iterations that is passed, times the number of data samples xi computed per f, which is usually the mini batch size or SGD, divided by the real wall clock time since the algorithm has started. Pretty simple definition. And throughput, we normally think of that as constant throughout the ML program's lifetime, right? Because the hardware is not changing and we're keeping the mini batch sizes the same. It used to be for a particular class of models. Anyone recall recurrent neural networks? Recurrent neural networks, when they were the hot thing for NLP, they had this property where the sequence length would affect the number of layers you'd go through, right? Because you repeat a recurrent unit once for every token in the sentence. So if you were using recurrent neural networks, throughput was actually not constant. It was dependent on the size of the sentences or paragraphs you're feeding at any given time. But for computer vision purposes and for transformer-based natural language processing purposes, computer vision, we have a fixed receptive field. In NLP with transformer models, we have a fixed sequence length, and it's not affected at all by whether you have use 10 words out of the 1,024, you use 500 words or use all 1,024, that doesn't affect the compute time of a transformer model. So throughput, by and large, consistent throughout ML programs' lifetime, in theory, except for recurrent neural networks. Okay. However, throughput can be uneven across workers, and this is something we need to be aware of when dealing with distributed parallel systems. Despite having identical hardware, what you may see is that there may be minor fluctuations in the time required to compute each iteration of a program, and this adds up to this jagged edge that you see at the front. What happens is that, what this means is that the more devices you throw at a parallel program, you do not get linear speed up. Putting it in, say, 16 times the devices will never get you 16 times the speed up. This is one of the reasons. These minor fluctuations are generally caused by things like the operating system doing things in the background. Sometimes users are logging in, sometimes there's asymmetry from workloads, but a more surprising factor is that heat, the amount of heat in the data center plays a role, because all modern CPUs and GPUs are basically throttle themselves once their thermal limits pass a certain threshold. So if you have uneven or poorly cooled data centers, and of course, you know, the big providers like Amazon, hyperscalers, Amazon, Microsoft strive to prevent this from happening. But let's say you're using your university cluster, for instance. If your university's data center is not well designed, you may have hotspots, and any machines sitting in that hotspot are going to be slower than average from the other machines. So many things can happen, and they can add up over time. Even a network switch, depending on how it's prioritizing packets, it could cause one set of machines to be slower than the other. Okay, so uneven throughput leads to something called the curse of the last worker, where the time needed to complete each iteration, because everyone has to exchange gradients before we can move on, is going to be a bottleneck by the slowest worker. So when the number of workers increases, what happens to the average time needed to compute one iteration? Fun mathematical fact, given p random variables with a uniform distribution between A and B, the expected maximum is given by this formula. And this formula basically increases with the number of workers P in it. More workers you throw in, the time needed for each iteration, the average time goes up. Okay, and then basically what this means is that in an ideal world, you get this black scaling line going from single CPU or GPU to multiple CPUs or GPUs in a single machine to multiple nodes distributed parallel. Ideally, we want to see this line. The line is actually linear, but it's shaped this way because the scale is a little bit different on the x-axis here. But this is basically a linear scalability. In practice, you never get that. There's a drop in scalability going from one GPU to two GPUs because now you have to deal with this curse of the last worker. And then, maybe you'll get this sublinear curve up to the maximum number of GPUs in a single machine. And then when you go to two machines, again, you experience a less than ideal scalability increase, because now you're dealing with the fact that the network is slower than the NVLink connection between GPUs. Okay, and that's the green line is the best you'll get with well-implemented, well-designed strategies and well-implemented software. What you want to avoid is the blue line, where you go from one GPU to two and you actually get slower, or you go from like n GPUs in one box to two n GPUs in two boxes and you get slower. By the way, Fun fact, I teach a class on parallel and distributed learning in my university. When I make the students implement projects, they always see this, right? I'm going to grab Megatron and Deep Speed and apply it to my vision transformer. And this is the first thing they see. I went from one machine to two and I got this drop, right? So this is not easy. And this is where most of the research in parallelism is focused on fixing this blue line here, where you get a drop rather than an increase. Okay. And if you get the red line, which no one does these days, but it actually happened a lot in the early days of parallelism. Famous example was the Mahout library in Hadoop, which was one of the first parallel machine learning libraries. At that time, people were not fully cognizant of the architectural disadvantages of Hadoop when it comes to machine learning. I'm not going to say too much, but the red line is what happened. Okay, so basically most of this is we want to avoid blue line and get to green line. Statistical efficiency. So we're going to compute this as the objective function at the current iteration t minus the objective function at the previous iteration or some number of iterations ago. We want to average that over many iterations. And we're going to divide it by the window size. That's 1 in most cases, basically the previous iteration, or S if we're going over multiple iterations, times the number of data samples used per F, right? So we're literally measuring the average rate of change in the objective function per data sample. And this is done empirically because we need something that's quantifiable in order to tune system performance, right? So stat efficiency, or the negative of stat efficiency, is essentially the tangent line to our theoretical rate of convergence in the ideal case where the theoretical rate of convergence matches our empirical, what we see empirically. And like throughput, there are different regimes. You may have the classic convergence curve, which is up, straight, and to the right. But in reality, we do see neural networks. I believe ResNet is one of those networks that tends to exhibit this multi-step convergence pattern. Also tends to happen a lot for more complex neural networks due to the phenomenon that there are, the theory being that the optima lie in some wider basin, and then within that basin there are many peaks and valleys, and then there's a phase where we're trying to get within the basin, and there's a phase where we settle into one of those little valleys, right? And then what black is okay, green is also okay, red is bad. Red means you set your learning rate too high, basically, right? So you want to avoid that. But learning rate is one of the tuning parameters in parallel and machine systems, so that's why we're mentioning this. Now, the most important thing is that throughput and S statistical efficiency may compete when we're doing parallelism. Because take, for example, a tuning parameter like batch size. If we increase the batch size, what happens is that GPUs have what we call higher arithmetic efficiency. For example, a GPU that's only been fed a batch size of a macro batch size of 1 may perform at like 80%, but if you give it a macro batch size of 4 or 8, it may perform at 95%. Right? So you do get a throughput bump by increasing the batch size per GPU. But as we all know, stat efficiency, when it comes to very large batch sizes, the amount of progress you make per iteration can only go so high, because what happens when you increase the batch size in SGD? You are eliminating noise in the gradient. What happens if there's no more noise to eliminate? Then your extra samples are wasted. But stat efficiency is progress divided by number of samples used per batch. So you're actually making less effective use of each of those samples. Okay, so and so this is why there's a trade-off between throughput and stat efficiency. Increasing the throughput, for example, by increasing the batch size, usually results in a drop in stat efficiency. But what the actual training performance is the product of the two of them, right? It's the amount of data you're churning per second times the quality of progress you're making per data sample. That's throughput times stat efficiency. That's the red curve over there, right? So what we actually want to do in systems is to find that sweet spot, which is the part where this product of the two curves is maximized. Okay, let's talk about a bit more about how throughput and SC compete. I talked about batch size, and this is an example. When we go from a batch size of 1, when we go to one device, in one device, there's no communication to speak of, to 2 devices, we will incur, although the computation time will logically halve, we now start to incur communication cost. If your batch size is really small, what happens is that the compute finishes really fast, but the gradients, it's still the size of the model parameters and you send them over. If you had a large batch size, on the other hand, you would take, proportionately, let's say you have 10x the batch size, then okay, your compute time is 10 times larger, but your communications time is actually still the same amount as it was in the first part. So the y-axis here is a different scale. Why is that so? Because when you have a batch size of 10 versus 1, you add all the gradients together on the GPU and then send some of the gradients as the message to the next GPU. So small batch size results in a lot of communication overhead relative to compute. In large batch size, the compute part grows while the communication part stays the same, and that results in the overhead due to communication shrinking. Okay, so and this is why with a overly small mini batch size, you get a problem where adding more compute devices doesn't give speed up. So generally in data parallelism, you have to increase the mini batch size as you increase the number of devices. In fact, you cannot have a fraction of a data sample per device. So there's also you have to meet the constraint that if you have X parallel devices, you need at least X data samples in your SGD mini batch. Okay, but then what happens with stat efficiency? So as you try to increase the batch size, ideally, if I 10x the batch size, I should see a 10x drop in the number of iterations needed to reach the same convergence threshold. But what happens is that this is only true for a regime of rather small batch sizes between 1 to 10 or maybe 1 to 100. As soon as you start going to thousands, this curve pulls away in a bad way, which means, and what's happening here is that the amount of noise in the gradients is already so low that increasing the number of data samples does not help you get more accurate gradients. So your gradients are not actually more accurate or better quality, but you're expending more data samples to compute each step. And that's why the number of iterations to converge actually increases, right? So this is why people are very careful about large batch training in particular. But the conundrum here is that we need large batches for our large scale, like hundreds of GPU systems to actually operate well. Okay. And here's a little bit of a pictorial depiction to explain why SE, stat efficiency, and throughput are at odds with each other. When we get near convergence, by definition, stat efficiency is low. It's a tangent line to the curve, so it's very flat. And this happens because individual gradients become very noisy near the optimum. When you get to close to the optimum, every gradient, every data sample's stochastic gradient is going to point in a different direction. And what you're actually taking is the average of those directions. That's your descent direction. But since the individual gradients are noisy, interestingly, if we increase the mini batch size while we're close to convergence, and say put in a lot more gradients, the average direction is going to actually improve quite dramatically. And then on balance, stat efficiency has this interesting phenomenon where the closer you are to convergence, the more you can get away with a large batch size, which will improve throughput without hurting stat efficiency too much. Okay, whereas if we thought about the ML program being far from convergence, say this part here of the sharp line means that we're making a lot of progress, and that's because the gradients are actually pretty much accurate when far away from the optimum. So what this slide is saying is that when you are close to convergence, you can actually increase the mini batch size, and there are systems that actually do this for you. Because what this means is that the closer you get to convergence, the bigger the batch size you can use, which means the more parallel devices you can throw at the problem. So the biggest implication of this actually happens at cluster workloads, where imagine you have many training jobs or hyperparameter tuning jobs going at the same time. You can actually strategize a cluster by shifting more GPUs to jobs that are near completion and giving fewer GPUs to jobs that are still at the starting point of their convergence climb. Okay. All right, and then finally, good put is just a product of throughput and stat efficiency. And that sweet spot curve I showed is essentially the good put curve. We are ultimately trying to maximize this. We're not trying to maximize throughput, neither are we trying to maximize stat efficiency. What we care about is how fast the program completes. And that's done by maximizing the product of the two. Okay, and then good put, the way you can interpret this is that it's really the amount of useful throughput in the system. If we were to normalize, so stat efficiency is normally not normalized, but if we were to normalize it between 0 and 1, we can think of it as the quality of the throughput, right? 1 meaning that every data sample is contributing the maximum amount to the objective function progress. 0 meaning that, well, you're probably at convergence anyway, right? So to forecast, so in ML systems, there is, in these high performance systems, there is a idea that if we can forecast the good put of a system, we can make the correct hyperparameter tuning decisions, like what is the batch size, number of GPUs, and learning rate, to maximize the speed of the ML program while balancing it with all the other jobs that are going on a single cluster. So to do that, however, we need to develop models of throughput and stat efficiency. So what I'm going to show on the next few slides is just a little bit of insight into how a sophisticated ML system thinks about throughput and stat efficiency. So when throughput is actually modeled by a model that looks like this, we call it an alpha beta model in the computer systems literature, where we basically take a bunch of terms and we collect data on how many iterations per second a machine can pull off. And then we fit parameters such as alpha and beta to this based on empirical data. So this is basically a simple linear model fitting problem. And this works because throughput is more or less consistent across every iteration. The only time it changes is if you change the number of GPUs or the mini batch, which is A, or the number of mini batches, which is M. Sorry, the mini batch size, which is M. Now, stat efficiency is a little bit more interesting. How do you model something that's actually empirical? Well, as it turns out, there is, and we don't need to study the math too much here, but what you need to know from this tutorial is that the concept of gradient noise, which is basically, are the gradients all pointing in different directions, or are they all pointing towards the optimum? The concept of gradient noise can actually be estimated. And the way you estimate it is via something called the gradient noise scale or preconditioned gradient noise scale, which can be done empirically by basically taking higher order equations based on the gradient G, the empirical covariance of the gradients, and something called a preconditioning matrix. For the purposes of this tutorial, when P equals 1, that's the equation for vanilla SGD. When you're using Adam or other optimizers, that's a different P. I'm not going to get into the theory of this, but essentially there is a way to compute basically the noise to signal ratio of a gradient just based on watching the gradients that have gone through your system for the past T iterations, for instance. And by measuring this PGNS, you can plug it into an equation to calculate the change in stat efficiency you would expect to get if you go from batch size M0 to M. So basically you are deciding, when can I increase my batch size? And because I started with a small batch size at the start of convergence, now I'm close to convergence, when can I increase my batch size? You can develop a model like this based on the recent gradients, compute the PGNS phi of T, and then plug in the batch size numbers that you want, and it will tell you what's the drop in SE you will experience, or you're expected to experience if you increase that batch size. And this is actually a powerful technique that's used in scheduling systems to optimize how GPUs in a very large cluster are allocated to different training jobs. Okay, so that was the background of the tutorial. We are now going into the second part of the tutorial. Well, I'll spend a few minutes introducing this topic, and then I'm going to switch over to my collaborators who are on the line. Okay, so when thinking about parallel ML, at least I personally like to think of there as being 7 systems aspects. These are choices we make in the system architecture or design that influence the performance of a parallel ML program. We have the computing aspects of message encoding and update aggregation. This is where techniques such as quantization and sparsification live. This is where we decide, do we want to use a parameter server architecture, or do we want to use a ring or reduce architecture for communicating messages? There's communication such as topology, which is often very much influenced by whether you're using, say, a PS or an all reduce, bridging and consistency models. We also have memory management issues because, like I said at the very beginning, you can't fit the whole model or even the activations on the GPU. So we need to think about how to chop up those model parameters data across GPUs, which is also intersecting with data model and pipeline parallelism. We also need to think about how the storage hierarchy is managed. Which is basically you've got RAM, you've got cache RAM, and you've got SSD storage. You've even got data that lives over the network. How do you manage all of this? You have, after all, those of you who may have programmed your own data loader in PyTorch would probably be a bit more familiar with this issue. You need to think about how data actually gets to the GPUs. And then you have execution scheduling, which is something that, for example, what I talked about, the compute graph partitioning in inter and intra-operator parallelism, that just specifies how to partition work to GPUs. But what order to have those GPUs executed? In a compute graph, the graph may branch and then contract and branch and contract. Do I tell the GPUs to go breadth first search or depth first search? That's execution scheduling for you. Okay, so that's just a kind of an overview of what systems people think about when they design these high performance training systems. And then ultimately, the message I'm trying to communicate is that to understand an ML system, it mostly suffices to understand what strategy it's using. And that strategy is basically composed out of picking instances out of each of these aspects. What do I mean by that? Basically, take something as classical as a parameter server. For those that are not familiar, parameter servers were one of the first large-scale model training systems invented before deep learning, but also used famously in Google's Disbelief, which was around, I think, 2012, 2013. Disbelief, where Andrew Ng and his team implemented basically a large deep neural network on a lot of CPU hardware. The way these parameter servers work is that there's a central set of devices that are responsible for performing the aggregation F. They take gradients from all devices, do the aggregation, and push the gradients back to the machines. So by and large, any parameter server, and there's many flavors of them, but you can boil them to basically a list of the aspects, or rather aspect instances that they do, right? For example, they compute messages if it's an SGD, you're going to compute basically something I call naive difference computing. You're going to aggregate them in a centralized way in a star topology. There's one parameter server and all machines are talking to it, and it's talking back to all machines, and so on and so forth, right? The point is that it suffices to understand a system through what strategy it implements. More visually, right? A parameter server takes, it splits the data. It's a data parallel strategy. So it splits the data to different machines, but it replicates the model on each device. And there's also one central device with the master copy of the model, right? And that results in this star topology of communication where everything's talking to a central machine and back. Message encoding is just the sum of gradients. Every machine sends its gradient over. The central machine sums them together, and then which is the update aggregation, and spits it back out. So this is basically a one-for-one mapping to parallel stochastic gradient descent, and that's actually why the parameter server was a very popular architecture. These days, though, these more decentralized architectures, such as ring or reduce, tend to be used because the problem with the parameter server is that it requires you to dedicate some central device, store the parameters. Okay, right. Now let's compare to something like ring or reduce, for instance, which ring or reduce is a communication strategy that's often used in, for example, NVIDIA's NCCL library. So when you train a machine learning model on 8 or more GPUs, say, or 2 or more GPUs, most likely under the hood somewhere, some ring or reduce call is happening, right? So here, it's a data parallel strategy. So again, it splits the data and replicates the model. But a comms topology is not a star topology. Here, every device is equal to all other devices. There is no central device. So the devices talk to each other along a ring topology. They basically forward messages to the next device in the ring, and the ring is closed, so it comes back to the first device eventually. So instead of sending the gradients over and aggregating them, ring or reduce actually does something that's essentially a running sum of gradients. Gradients from machine 1 are passed to machine 2, they're aggregated, and that running sum is passed to the next machine, and it snowballs all around the ring until it comes back, right? This is a bit of an oversimplification of how it actually works, but the important thing is that by just examining the aspects of ring or reduce and comparing it to parameter server, I've described the difference between the two strategies, right? And so this is how we can think reduce systems to essentially a more abstract understanding. And from there, we can decide, is this the right choice for my parallel ML workload, or should I be choosing something else? But the more important development is that these pure strategies are no longer the best way to actually run parallel ML programs. There is something called a hybrid parallel ML strategy, in which we take say a complex deep learning program and apply multiple parallel ML strategies to different parts of the model. The case for this is kind of intuitive, right? A lot of model architectures are fairly heterogeneous, and I'll show an example in a little bit. And these heterogeneous model architectures, they may perform one set of layers, may perform well under one strategy, but that same strategy, if taken to the middle layers and upper layers, may perform poorly. And we'll show an example in a little bit, right? And it's also the case that some workloads are so large that pure data or pure model or pure pipeline parallelism is insufficient, and we have to combine two or more of these strategies together. So in a hybrid parallel ML strategy, we can combine, for example, two data parallel strategies, like a parameter server on one part and an all reduced on the other, or different parallelism types, such as data, model, and pipeline parallelism all in the same program. In fact, for that matter, something like GPT-3 or 4 is trained using a combination of data, model, and pipeline parallelism all at once. So for the very largest, the larger the problem gets, or the more complex your model architecture gets, the more combinations of strategies you will have to apply to the same model, because using these different parallelism types will mitigate their pros and cons depending on which part of the architecture you're looking at. So I'm going to come back to this slide in a little bit, but first let me show you an example of how a hybrid strategy can improve performance rather than using a single strategy for the whole model. So take, for example, the classic LXNet. At the start, you have convolution and pooling layers that get progressively smaller until you hit some fully connected layers at the end, which is basically performing the multi-class logistic regression. So in a typical convolutional neural network, you have few parameters in the convolution of pooling layers, usually less than 1,000 floating point numbers. But in the fully connected layers, that's this giant weight matrix, like 496 times 496 in the case of LXNet, and that's like 100 million or so parameters. You have a huge number of parameters at the end, a small number of parameters at the start. That gets you thinking, do I really need to use the same strategy on both? As it turns out, parameter servers perform better when the number of parameters is small, because they are kind of a centralized architecture. Whereas there are different types of strategies, such as all reduced or sufficient factor broadcast, that are more adapted to dealing with large number of very large matrix parameters. In particular, sufficient factor broadcast is essentially the idea that you do for most what call affine transformations, AX plus B, the stochastic gradient of one data sample turns out to always be a rank 1 matrix. So if you don't have to send the matrix over, you can just send the two vectors for the rank 1 decomposition over the network. And the disadvantage of this is that you can't add these rank 1 vectors together. You have to send each of them individually. If you have a batch size of 16, you have to send 16 messages across the network rather than a single gradient sum. But as it turns out, these vectors, if you have a 496 by 496 matrix, that's 8,000 elements if you send the vectors, and something like 16 million elements if you send the actual matrix over. So there's a potential for huge savings under the right conditions. And the point is that by applying a parameter server to the convolution and pooling layers, but applying a different strategy such as sufficient factor broadcast to the upper layers, what happens is that you can gain up to a you can gain up to a between 2 to 8 times throughput improvement on convolutional neural networks just by specializing your strategy for different parts of the network. Okay, so this is, in fact, this is the basis for modern parallelism in deep speed and Megatron, where different strategies are actually applied to different parts of the network in order to get the most performance possible. I'm going to shuffle back to a slide I just showed here, but essentially the way we need to think about data, model, and parallelism at a high level is that they have pros and cons depending on which dimension you look at. Implementation complexity, data parallelism is considered the easiest to implement. It's any first-year grad student can do this. Model parallelism, as we've shown from that alternating row column partitioning example, requires a fair bit of expertise to pull off. Pipeline parallelism is a little bit simpler just based on my observations for teaching classes and seeing class projects. And now constraints on model size, data parallelism, you can't handle large models that are bigger than device memory. You also need the minimax size to be equal to or greater than the number of devices, right? Hard constraints, model and pipeline parallelism, good at handling large model parameters, which is kind of why you need to marry data with model and pipeline parallelism if you're going to tackle the largest training problems possible. Load balancing has its own set of issues. Data parallelism is easy, model and pipeline parallelism, you have to think about how to chop up different pieces, and that's not always trivial, depending on the complexity of your architecture. Communication volume data suffers from this problem where you send the whole gradient across the network. Model and pipeline parallelism, if implemented well, can reduce the comms volume, with pipeline being lower than model. That has an implication. What happens is that in very large training problems, you usually use model parallelism within a same machine where you have NVLink between the GPUs, but you start to use pipeline parallelism between different machines. So it has implications. Okay, and communication latency is also an issue. Data and model parallelism have low to moderate latency. That's the amount of time it takes for one data sample to go through. Pipeline parallelism, because of assembly line nature, takes a long time for one data sample to finish all of its computation, which actually makes pipeline parallelism great for training, which you don't care about the latency of a single sample. And it turns out to be not that great during inference or serving, where you might care about how quickly you can get the response of ChatGPT. You definitely don't want to use pipeline parallelism there. Okay, so these are the considerations that motivate people to cross and combine different parallelism strategies in a complex model. And this Alex example was just a simple teaser of what people do. Okay, now, and I'm on to the final set of slides before I hand over to my next presenter. So we talked about these hybrid parallel strategies, but in practice, what if I'm not an expert at this thing? What if I'm not smart enough to make the kind of strategy I just showed on AlexNet, for instance? Or what if I come up with a new model every like 3 months in my lab, and I just want some software system to do it for me? Well, you're in luck, because there are actually software systems that compute these strategies these days. It's an active area of machine learning systems research. So the idea is that, remember, at an operational level, these autodiff systems operate at the compute graph level, and they do some basically intra-operator, inter-operator parallelism. I talked about that at the beginning. So it turns out that you can turn that into a search problem, right? Why not search for the best way to perform inter and intra-operator parallelism, right? For example, intra-op parallelism is, do I row partition or column partition a matrix, or do I even replicate it, right? What's the best way to color each of these boxes so that I get the maximum speed? And then what's the best way to cut the graph up and give it to different GPUs or CPUs so I can also improve the speed further, right? And it turns out that, you know, if you, by combining intra and inter-operator parallelism, which is say I data plus model plus pipeline, I get the green bar, which is superior to using intra-op only, which is data/model parallelism, or inter-op only, which is pipeline parallelism. Okay, and example software takes the compute graph of a machine learning program, so as and then it just searches over it to find the best way to parallelize it. And this is basically means that no human effort is needed to create the strategy. And the way it works is actually via a two-stage hierarchical optimization pass, where it alternates between an inter-operator pass that's figuring out the pipeline stages, and intra-operator pass that's figuring out the data and model parallelism, or the more exotic forms of parallelism that are neither data nor model. And then once it's done optimizing the graph, it comes up with this partition compute graph, where every node is annotated with, do I do it in a row partition way, or column partition way, or what partitioning? And then the graph has annotations such as, this is stage 1, this is stage 2, this is stage 3. Then it's passed off to the autodiff system, which then says, okay, I'm going to read this plan given to me by Alpa, and then I'm going to set up all the GPUs and then compute this plan. And that's automatic parallelism at a high level. But what actually happens in the search is that you take the compute graph, you divide it into some sort of search space. You have to figure out the pipeline stages. So do I put A and B together and then C and D in another GPU? Or is it A, then B, C, D in the next GPU? That's figuring out the pipeline stages. Then within a particular stage configuration, you then go down to the next level. For every operator in the stage, do I row partition it? Do I column partition it? What kind of partitioning do I do? Okay. So the inter-operator pass, basically is the first pass that happens. Whole compute graph, we come up with different candidates for graph partitioning. Maybe the top one is very unbalanced. Stage 2 and stage 4 literally have one operator. So we're going to adjust that to be the bottom one, but now stage 3 is only one operator. How this actually works is that, let's see if I have the right slide here. So how this actually works is basically by a dynamic programming problem, classical computer science problem, where we have a way to use cost models to estimate the throughput of each stage. So a while back, I flashed a slide on the throughput cost model, what I call an alpha beta model. That's essentially what's done at a very large scale in order to estimate for each plan what's going to be the cost of each stage in compute and communications. The point is, if you can measure it, you can search over it, right? Same thing we do in machine learning all the time. So that's the inter-operator pass. It's going to find the best way to partition the stages. And then those stages, each is going to be assigned to a set of GPUs. Maybe I'll assign stage 1 to 8 GPUs. Maybe I'll assign stage 2 to 2 GPUs. The point is that you can be that fine-grained. You can assign heterogeneous numbers of GPUs to each stage that's expressible on the search problem. And then the goal here is, because this stage is about pipeline parallelism, it's really about minimizing the pipeline execution latency, or put another way, what's the imbalance in pipeline stages? You want to get perfectly load balanced stages, so you don't end up with this problem where if a later stage is shorter than the earlier stage, you get this period of idle waiting time, and that's no fun and it's bad for performance. You want to get all these stages as even as possible. That's the goal of this inter-operator pass. Then after you do an inter-operator pass, you're going to take each stage and run a sub-search on it. That sub-search is going to say, I've got a stage, I've got some number of GPUs given to me by the inter-operator pass. I'm going to now decide row, column, partition, replicate, or other forms of exotic partitioning as implemented by the system, right? And this turns out to be an integer linear programming problem. It's a kind of discrete math problem, but it can be searched, right? With heuristics of approximations. And you actually come up with a plan. I'm going to row partition, column partition, or alternate them in a clever way. Again, the models minimize compute, minimize communication time, right? And then, well, that's exactly what I said in this slide. And then the thing that you need to know is that under the hood, for every operator, say take a map matrix multiplication, the creator of this alpha system has to implement what are the possible parallelization strategies for it, which is, in the case of a map mul, it's basically row partition, column partition, or replicate and reduce. So there's basically three basic strategies. Not going to go into a little bit too much about them, but the point is that if you have a convolution operator, now I need to implement that. So this is kind of akin to when TensorFlow or Caffe first came out so many years ago, where people had to implement every operator from scratch, right? You had to implement the CUDA kernels for all of them. Well, that's what's happening now, but at the automatic parallelization level. For every possible operator in a compute graph, people write down what are the possible strategies and what are the constraints of those strategies. Like if I do a row followed by a row, I have to communicate. If I do a row followed by a column, I don't have to communicate. That's expressed over here. Like, for example, there are rules that say row to row. Well, this is actually a row to column, but the point is that sometimes you have to repartition and communicate, and sometimes you don't, right? All of this is built in, hand-coded, operator by operator, rule by rule in the system. But fortunately, there's only a finite number of operators we have to use in deep learning. Eventually, you'll get them all, just as TensorFlow and Caffe got them all at one point. And basically, by building up all of these and the different rules, that provides the search space for the intra-operator pass to go over and figure out what's the best partitioning strategy for every single operator inside a single stage. Okay, all right. So this is now the end of my part of the tutorial. And I'm going to let my next presenter take the stage here. So, Hogi, are you there?
Yes, sure, I'm here.
Great. Again, sorry that we bled a little bit to your time because of the IT problems earlier. So what we can do, I think, is if you can go for, does anyone know when the coffee break is? Is it happening right now? Okay, why don't we do this, Hongi? Let's have the audience go for their coffee break first, and then in 15 minutes, we will restart the tutorial. How about that?
Sure, that sounds good to me.
All right.
So how long is the coffee break, by the way? It's like 15 minutes.
We're breaking the audience, but I think the audience break for 15 minutes, 15 minutes.
All right, yeah. I guess we can start at roughly speaking, I guess 1:20 for me, but it should be what, like 10:20.
Yes, your 1:20 p.m. in Eastern time.
Yeah, sounds great.
Is it not coming through the speakers? It's probably because I didn't press the right buttons on this device. It used to be. Oh, hello? And no, it's because I wasn't standing near enough to the mic. That was all.
You're sounding fine. I don't think there's here in Zoom. You need to somehow give the Zoom output to the.
But that's okay because my laptop mic is actually transmitting. So the people on Zoom have been able to hear all this time, as I understand. So
What do you mean it's here when they're talking, we want the speakers.
I'll say that again, right?
So when your full speaker is talking through Zoom, we want to hear it. Not
Oh, yes, of course, of course. Let me do a little bit of tests with my fellows over here. Thanks for the reminder. So Sam or Hongi, I'm sorry, are you still there? I think I need to do a little bit of my speaker
Yeah.
test over here. So yeah, so Sam, I need to do some tests here to get the speakers to
Okay.
project. Let me change my audio devices. So let's try this. Okay, Sam, can you say something?
Yeah, 1, 2, 3. Can you hear me?
Okay, looks like we fixed the problem. Audio is coming in. Oh, seriously, it's coming from there. We'll need to try this again. Wow. Oh, well, the absent PJ is that little projector there. And I think I am going to have to call for IT.
I think so if you go on the top, on the, there,
Where?
where the
Your
mic.
Mike.
your sound.
I don't know. I don't know what they're doing, right?
Yeah.
Your sound.
Yeah, so
Yeah,
the
so
device, this device has somehow not been discovered, even though I've connected it now. Maybe it's because I didn't press the power button.
No, I think that device is okay. We need to just call the
Yeah.
IT. Yeah.
It's okay. I got 15 minutes. I'll figure this out.
You did a great job recovering, by the way.
Yeah,
Incredible.
adventurous, but no, thank you so much for the adapter. That the fewer minutes I have to spend with a blank screen, the better. Okay, yeah, so Sam, I apologize, I'm eating to your break, but bear with me for a little bit as I try to get this microphone
Sure.
system do its job. Probably some detection issue. Where is my? Yes. Do you have a question? Sound, yes, sound. Is it this one, right? Oh dear, is it not going to detect itself? In fact, now that I think about this is actually a microphone, and this is a microphone. So these are actually separate microphones. So this thing is not even connected to this microphone.
I see.
Yeah, now that I think about it, this is a mic device, and this is a mic, and okay, I'm gonna have to call IT because clearly they didn't think this through. Oh, and it came to life. Why? Let's see. Oh, maybe if I switch to my speakers. Okay, Sam, can you try to say something again? Do another speaker test
Let's
here.
see. Does it work now?
Can you say something
Yeah,
again?
Yeah, is it better or no? Yeah.
I have not figured out
Yeah,
how
can you
to.
hear me?
Oh,
All right.
I think I see the device now. Let me try this. Okay, can you say something again, Sam?
Yes, so can you hear me now? Good.
Is this loud enough for you people at the back to hear? Sam, can you say something again?
Yes, hi everybody. Can you hear me?
Affordable for people in the back?
Yeah.
Excellent. Okay, yes, thank you so much, Sam. I've gotten one of the devices to work, so this should be good enough. Okay,
All right.
I'm going to break for now and I'll be back. Yes, we've managed to get. Okay, is that? Yes, hello. So I just want to understand something. So right now I'm using this speakerphone to broadcast my virtual presenters. Right. Ideally, we'd like that to be hooked up to the real powerful speaker here, but as I understand, this is hooked up to that. It is hooked up. Yes. Really? Because I don't see any wires going between the devices.
Yeah, across the floor to the speaker.
Right, but what's happening is that this device, which was provided to me by the conference, right? This is where my remote speakers emit their voice. Right. But there's no closed loop
as far as I can tell, between this and the microphone, right? Because this microphone is not.
That's going straight to the speaker.
Okay, well, it's okay, then there's no problem. I think this is loud enough. This thing is loud enough. It's just that we're not going to be able to use the speaker.
Right, or you just could like aim this down closer to that. and
Oh, I
pick
think
up-
that would cause a feedback
Yeah.
loop. I'm worried about that. So maybe I'll avoid doing that. But for now, it's good enough.
Okay.
Oh, hello, sorry to bother you. We were just
No worries, yeah.
figuring out. Yeah, we're just figuring out how it turns out that this speakerphone is not in a closed loop with this microphone at all.
That's right.
And I have virtual speakers, so and those virtual speakers will be emitting their voice through this speakerphone. And we were just deciding, should I like analog and tape these two together? But I think not. So we're all good for now, I think. And sorry
Right.
to bother you.
Yeah, no worries. Yeah, if you have to, then you could
Yes.
just aim it over that direction.
Right. We'll see.
Kinda makes-
We'll do that if we has to come to that. but
Yeah.
I'm worried about feedback.
Well, right. That's the big issue of it. Let's crank this guy up here.
Yeah, I think we got it. Max, then I did a mic test earlier and looks like folks at the bathroom can hear.
They can hear you. It's not that big a room. Yeah. All right. Very good.
Thank
Glad
you.
you're all set.
Yes, it's all set. Okay.
So, Chirong, are you there?
Yes, Hoagie.
So, yeah, so someone there just discuss a bit. It seems like we are overtime a little bit, or maybe just kind of like 30
Yeah,
minutes.
we are, I apologize, we are over time due to combination of factors. Now, so the last part of the tutorial is going into lunch hour. So so technically, if we officially we had the tutorial end at 11:45, right? When once, so we between 10, so I'm talking about local time here in Vancouver, 10:20 is when the people come back from their coffee break. 11:45 is supposed to be our official ending time, but really it's flexible because the way it works is that that's just the start of lunch hour. So what we can do is we can kind of unofficially push the tutorial out by another 15 or so minutes, however many minutes we need. And it'll be up to the audience whether they want to stay back or go for lunch. But lunch hour is like 1.5, 2 hours long. So that's one option. We have to recover from the mishap earlier.
Sounds great. Sounds great. Yeah. Just
Yeah,
want
so
to make sure we
Okay,
have a
I'll-
plan.
Worry
I'll
too
also
much
try
about-
to go a bit faster then.
Yeah. Sorry about that, guys. And again, don't worry too much because right after us, there are no tutorials. It's just lunch hour. So it's
Okay.
possible to bleed a little bit with that. Okay, I need to go for my break now. I'll be back.
Sounds great. Great talk, by the way.
Yeah, thanks. Hey, going, yeah, it's, gosh. I do a lot of like smaller modeling, or type B. Model. My toe and figure out where it's. Yeah. Ready for you. I'll take some stuff back, yeah. I think. Sure.
Yeah, I think 30. The Federated learning aspect. Yeah. There won't certain time here. Yeah, so I actually took that data a couple years ago to find for satellite based research. And it wasn't all like machine learning focused, but maybe attending, okay, and like there, they were doing. Oral. I'd say like it's over there. Oh, cool.
Okay, so Hongi, are you on the line?
Yes.
Perfect. Can you start to share your screen as I need to make sure it's showing up on the projector?
Right. Let me try to do that. Let's see.
Okay.
Can you see my screen?
Yes, that's perfect. It's showing up on the projector. Okay, and then it is almost 10:20 here. So in 1 minute, I'm going to kick off. So just wait for my signal.
Awesome. Sure.
Yeah, are you in like that? Yeah, I do. Very cool.
By the way, I'm not the host right now, right? I think I give it back to you. Okay.
Is that so? Okay. Let me pass the host on to Sam. It's just so that someone can admit people, because what's going to happen is I'm going to step away from the podium. So I will not be able to manipulate the Zoom. And if I did that anyway, it would show up on the screen. So Sam, are you back yet?
Yes.
Yes. I'm going to
Can we
make you the
start?
host. If you see people come into the Zoom room, could you admit them?
Sure.
Perfect. And then once your turn starts, you can pass the host back to Hongi. Okay. Okay, changing host over. And all right, Hongi, can you start your share again?
Oh, I need to start share again. It's not
Yeah,
okay.
because when you change host, it dropped. So let's see what happens when you
Got
share.
it. Got it. Okay.
Okay, let me try to full screen this again.
Is that working?
Yes, okay, we now see it. And let me amplify your voice a little bit. Okay, can you do a mic check, Holly, just before we go?
Hello, is my voice sounds right?
Okay, can I ask folks at the back, is this audible? Okay, we're good to go. Hongi, please take it away.
All right, awesome. Welcome back, everyone. Yeah, so this is the second part of the this tutorial, ML systems for large models and federated learning. So I'm Hongyi Wang, currently a senior researcher from the machine learning department at the Carnegie Mellon University. So yeah, as part of the what Qirong basically mentioned, his great introduction in the distributed training. So I'm mostly going to focus on in this part the inference and the serving of basically what's so-called foundation models. So we also cover the previously famous model, let's say the convolution neural networks, BERT, but we'll mostly talk about the autoregressive models for this part of the tutorial. So we basically talk about the several like optimization tricks for the decoding autoregressive model, basically incremental decoding and speculative decoding. And we basically roughly cover like a serving system called ORCAP. All right. So basically, let's talk about the what's happening in inference, right? So back into the in the old days, right? So-called kind of like old days, but CNN is still the kind of like dominating model. So what's actually happening in the inference is basically we're just doing part of the computation in training, right? Remember when we do training for a deep neural network, we're just doing forward pass and backward pass. We get a gradient, we update the model, right? That's kind of like a very standard workflow. But in inference, what we do is basically just do the forward pass, right? And we basically just get the probability output from the last layer, and we basically use the probability to just get the prediction label if we're doing the classification task. So actually for CNNs, it's not technically that different from training. It's just doing part of the computation of the training. And then we can just kind of like easily serve that like the model. And that's actually happening for every day, right? We're using the mobile devices, our cell phone. If that's running like a deep neural network, it's just doing the forward propagation like over and over again. So like people have come up with different techniques to optimize the inference, right? So say we can do something about the network, like we can do pruning, sparsification, quantization, or use low precision computing if our hardware support that. And we can also do some low rank factorization to basically just approximate the model weights. So basically overall, all we want to do is that we want to make the model fit in some small devices, let's say our cell phone, and do just the fast computation. So that seems to be easy, right? We can just batch input and process through the network. So what happens for the BERT and the vision transformer models, right? That seems to be coming a little bit after the convolution network. If you look at the input, it's a little bit different because currently we are in the BERT and the vision transformer model, we are processing the sequences instead of like each of the images. So let's say for this image, we're just splitting splitting that into different sub images and make that a sequence. And we basically just put that into the BERT or vision transformer model. Or we can also basically just process let's say the sequences. It's kind of like a sequence of token. Let's say this example CVPR is an annual conference on computer vision and pattern recognition, right? So that's kind of like different sequences, and we just kind of like tokenize the kind of like each of the words or kind of like a sub words, or just a character in each of the sequence into a kind of like a sequence of token. And then there's a kind of like one tricky thing compared to the convolution network is basically the sequence has its length, right? So if we kind of like just, especially for the like language example, if we kind of like pass sequence with different lengths, we will have to handle them like by, some just the zero padding, or maybe even more smarter padding, such that we can just put them as the same dimension. Then now it kind of like contains a different dimension, right? So kind of like a batch, sequence length, and also the embedding dimension. We just still we can do the same thing. We just pass those kind of like encoded and embedded sequences into the BERT model for vision transformer. Then we get the same thing. It's mostly for prediction, right? So that's the so-called encoder-based model. What does encoder-based model are doing? So roughly speaking, it's kind of like the convolution networks, the inference of BERT and Bayesian transformer is basically just taking a batch of sequences with some necessary care of those like sequence length difference, and then we can still do that. Again, we can also use the same techniques, pruning, sparsification, or whatever, just to make the computation a little bit faster, right? So that's a little bit complicated compared to convolution network. Then let's take things a little bit step forward, right? So what will happen in the GPT model? That seems to be the most kind of like, the hottest thing people are playing with every day, basically. So it's called the autoregressive model. I basically explain why that's the case and how it works. So let's say we are doing an example, right? So in ChatGPT, that's what we are playing basically every day, right? So I'm just giving the prompt saying, I will give a tutorial, right? So that's my prompt. So the model will basically, as a first step, just take all my prompt, right? So it's just a word token. If we are kind of like a content, each of the word as a token, it will basically say, it will basically be 5 tokens. Then we basically take all the 5 tokens once, and it will decode the next token, right? So it's kind of like, that's why it's called the kind of like decoder-based model. It's basically taking the prompt and all the previous part of the sentence and try to decode what's the next token. Then let's say the model give me an ad. Then in the next step, what I will do is basically I will just concatenate the ad here. So now my prompt will be, I will give a tutorial ad, right? So then the model just take all the previously generated, like containing my prompt and just the previously decoded token and compute the next token, right? Let's say CVPR, and then I just give it again, right? That's the third iteration, and say 2023, and then until we get something, right? So it's just kind of like the N token, the EOS one. So basically that's learned. So model knows when to kind of like stop generation. So we will keep generating until it gives us a kind of like an N token. So that's the whole thing called autoregressive model, because the model is just keep generating until it reaches to the end. So that's what's happening in the, back in the scene of the GPT inference. All right. So if we take a little bit closer look, right? So the first step is the same as the BERT and Bayesian transformer inference, right? Because we have the prompt all at once, so we can just insert them into the model and basically try to generate the the next token, and then we start the incremental or whatever, just the autoregressive decoding part. So each time we just decode one token, and we kind of like keep moving forward. So why does that make things challenging, right? So it makes things challenging because it's highly, so the decoding part is highly depends on the previous experience, right? So for each of the time, I can only decode one token from the previous tokens. And that also means the computation is hard to parallelize, right? So we can just only work on one token, and that's not quite GPU friendly, because our GPU wants to do what? Our GPU wants to do parallelize the computation. So we should actually parallelize the computation as much as possible. Think about the convolution network, right? We can just put as many images as possible into our GPU and just let the GPU run. But here, it seems to be a little bit hard. It's because of the dependency of computation. And also, the final sequence length is not quite predictable, right? We don't know when the sequence decoding will end, because that's sort of like learned, right? So we will kind of like wait until the model generate and keep generating until each reach to it kind of like give us the end of generation token, right? So that makes things hard. And also, plus the model is just large, so each of the computation can be like computationally expensive and also memory expensive. But that doesn't mean we can't do anything about that, right? So let me just tell you two basically quite popular and easy trick to implement in practice, and seems to be quite powerful. So first of the optimization is called incremental decoding. So what does that mean? It's basically, let's still use the same example here, right? So I will give a tutorial. So that's my prompt. I will just pass that into the GPT model. So let's take a closer look at what's happening in the GPT, right? So the most important computation in GPT is something basically called basically attention. So attention here, if you look at that, it's kind of like a simplified version. It's just calculate something very similar to the matrix multiplication. So the matmul here is kind of like there's the softmax in between, but it's kind of like roughly speaking, still the matmul operations here. And in the first step, we're just doing self-attention, right? So basically means the QK and Q query key and values are all the same. Then we basically just get this computation, and we basically just get the result in our next tokens basically add. Then we can kind of like take a closer look into this computation. It's basically the keys and the values will be used for generating the next token, right? So we kind of like use them anyways. So why don't we basically just save them into the GPU memory? So it's usually called cache memory, and then we kind of like avoid to calculate them again, because in the next like iteration for decoding the token after the add token here, we'll basically just reuse them. So the idea here for the incremental decoding is basically we're just use more GPU memory to avoid the computation. So it's kind of like a simple and intuitive idea. Then what will happen in the next stage here is basically we just take the add token, and since the key and the values are stored in GPU memory, we're just restoring them from the cache and just keep decoding, right? So otherwise we will have to compute the kind of like I will give a tutorial again for keys and values. So, you know, it's so this is kind of like a simple idea, but seems to avoid a lot of like recomputing with the cost of a little bit kind of like a memory. And then after this iteration, we'll kind of like rewrite it back with kind of like the, you know, keys and values with respect to the add like token back again to the cache memory. It's basically we just update the cache memory. But this is not the still kind of like when sequence becomes longer, it will still kind of like take more memory and the computation will become slower. So that's why as you kind of like as you folks are playing with GPT, you can see that's why GPT is a little bit hard to support very, very long sequence generation. This is kind of like one reason. But overall, this is a quite popular optimization. So the incremental decoding idea has been integrated into many inference engine, let's say the FAIR SEQ and the fast transformer and a lot of like library you're interested in. Basically, let's say deep speed and also fast transformer integrated lots of features in the Megatron LM library from NVIDIA. So that's the first optimization. Quite a simple idea, but turns out to be work quite effectively in practice. Basically, the second idea here is slightly different from incremental decoding, but it can take the idea of incremental decoding. But overall, it's kind of like using something different. So it's kind of like based on the observation, right? Some of the, so as human, we speak language with some specific patterns, right? So some of the like next word prediction can be easier, and some of them can be harder. Because, so like, for example, if I'm saying like the CVPR, so the next word is likely to be a conference, right? So, but if I'm saying something like a CVPR 2023, we host at, then the model has to figure out, right? CVPR this year will happen at Vancouver. So, you know, kind of like so the intuition here is that some of the pattern is easier to capture even by some smaller models, but some other patterns is kind of like hard. So we will kind of like really need some intelligent model to handle that. And also, if we can parallelize some of the computation, so the GPU will be happy because so GPU is currently memory bound, not the computation bound. So we can try to kind of like throw in the GPU as many as tokens as possible. So idea here, roughly speaking, is sort of like we use a small model to just doing speculative decoding. So basically just to try to guess what's next. Right. So if you're kind of like familiar with the chip design, it's kind of like doing the same thing, right? You're trying to predict what's the next, the result of the next calculation, and then you kind of like do some check. So currently in this scheme, the check will be done by the large model. Let's say the large model currently can be a llama, let's say 65 billion. The small model can just be like 6 billion llama. So the hope here is what? The hope here is the tiny model can capture most of the generation, and we only need to check that for a few times during the whole generation. So, so that's basically the whole idea. That's why it's called speculative decoding. So let's kind of like delve deeper to see how is that exactly works. So the step first is basically using the tiny model to basically generate gamma tokens. The gamma is basically here a hyperparameter. So so we talk about like usually how people can just select the gamma hyperparameter. Let's say the model generated 5 tokens here. So Japan's benchmark bond, right? So that's the very first step. So the second step here is basically we are just taking in the large model. But like remember, like when we have the problem all at once, we can do things in parallel, right? Because there's no dependency. We already know the sequence. Then we can do the checking in parallel, right? So the first step is basically just to check the first token, and the kind of like second step is we check the first 2 tokens, and so on and so forth. But the beautiful part is we can check everything in parallel. Then we just do this quite simple checking, right? So the simple checking is basically use this frequency. We'll kind of like discuss, but maybe hopefully you already see why this kind of like using this frequency here. We're just basically checking this frequency. That basically saying, if we are going to accept the token with this frequency, otherwise it has the probability to reject that. So what will happen if the token is rejected? Then we'll basically use a large model to regenerate that token that rejected using this kind of like modified probability. Again, we'll basically discuss why that's using that. It's quite straightforward actually. Then we basically just fix the rejected token using the large language model, and then we just switch back to a small model, right? So basically the thing works like this. The small model keep generating until a gamma token, and the large model will check in parallel. Then it will basically fix the token at the point it get rejected. And then we kind of like start from the fixed token and keep generating until we reach to the end of the kind of like end token. Then why we are using those probability, right? It's kind of like straightforward, because we want to, what we want to do in here is basically want this hybrid decoding framework that generate the sequence that is exactly as the large model, let's say the GPT-4. So how do we calculate the the kind of like probability, right? So there are 2 probabilities. So one probability is that we're using the small model to generate a token, and the token is accepted by the large model, right? So that's the probability. And what's that? It's basically the small model like a generation probability times this acceptance probability. And in the same way, we just do the same thing, right? And then if you just add them together, you'll find that that's the same probability with the target model, which is basically our let's say 65 billion llama model, right? So that's in probability, it should generate the same token with you just use the llama model, right? And let's walk through just a very concrete example here. So let's say the Japan's benchmark bond, and the bond is the large model finds that's not correct. Then we basically correct that. Then we just keep generating, right? And we just try to generate until we reach to the end. So in this example, we kind of like generate 31 tokens, but only with 9 rounds of the participation of the large language model. So that basically means we can, for most of the time, we just use smaller model to finish the generation. And then we just kind of like use the large language model for a few times to just check the computation. To basically, that basically turns out to save a lot of computation in practice. That this is, so here, the target model is the 11 billion T5 model. And turns out we can just use a very small T5 model. It's only 77 million. So like, in the end, they're kind of like generating a sequence with the same quality, but we kind of like reach up to kind of like 3 times, up to 3 times speed ups here. So that's the basic idea of speculative decoding. And so what about the hyperparameter gamma here, right? So that seems to be also quite interesting. It's basically, so here the x-axis is just the alpha. So alpha is basically mirroring how close the tiny model is mimicking the behavior of the large model, right? So that's something, if the smaller model is closer to the large model, then hopefully it's just that more kind of like the y-axis is how many tokens will be accepted in expectation by the large model. So we can basically see here, right? So it's roughly speaking have the exponential growth. If we kind of like make the smaller model closer to the large model, This is just mirroring the KL divergence. And then, like hopefully more tokens will be accepted by the large model. So in practice, it's still sort of like an open problem. How can you build a small model that's as small as possible, but as close as a large model as possible? So that's kind of like a open problem. But yeah, that's kind of like hopefully give you a rough idea on what speculative decoding is doing. So now I will kind of like move forward to introduce you kind of like a serving system for foundation model. It's called ORCAD. It's a kind of like a paper at OSDI 2022. I basically put the title here. So basically what's happening in a serving system is basically, so here the execution engine is something, let's say the fair SEQ and the faster transformer we just talk about. So that's just the library people can use, right? But in practice, so when we serve a model, we serve a lot of users, right? The user will just put their request, which is usually just a prompt. So the prompt will be saved in the request queue, and the system will basically handle how do we kind of like put the the computation together and just give them to the execution engine. And why do we need to do that? So hopefully we just improve kind of like improve the inference throughput and also the latency at the same time, so the user can basically just get their kind of response as fast as possible. So what usually the system is doing is basically just to try to batchify things and put that into execution engine. And if say the scheduler is smart enough, the user will kind of like get faster like response from the system. So why this problem is hard, right? Because hopefully I can like give you some warm up here. So the first reason is basically very simple, right? So because we can never predict how long kind of like a prompt we will generate. So let's say here the X1 is something like I think this is great, right? So that will kind of like take like the 3 or 4 like basically 4 decoding step if you contain the like the N token. And for the X2 generation, so the I love you case is basically just taking the one step of decoding or 2 step contains the end of the decoding step. So usually the system designed as the request granularity, right? So that basically means in this specific example, so the decoding of X2 will be blocked by the decoding of X1. So, that basically means the user, even if its request just need to decode for 1 token, you will need to wait until, because his or her request will just batchify with the wrong or inappropriate like user's prompt, it will kind of like be blocked. So, so one optimization can be done is basically we can just break the granularity into iteration level scheduling. So basically for each of the generated token, so the execution engine will be forced to return it back to the scheduler. And the scheduler will basically, the system will basically check, right, to see which like input is hit to its end, and it will basically just return that to the user and try to batchify the remaining like requests with other kind of like requests, or just let's keep generating. So that's one idea. So the second idea is basically it's really hard to batchify the input together. Let's think about this example. So here it's the X1, X2, X3, X4. So X1, X2 is basically, so gray box is just the user prompt, and the white box is generated token by the, let's say, GPT. So all those kind of like 4 tokens are basically like at the different stages that of like decoding. So let's think about, can they even be batchified together? It turns out if we are just using the vanilla like a system implementation, so none of them can be batchified. So here are just the 3 example basically. So let's say X3 and X4 is basically can't be batchified together. That's kind of like simple, right? So so think about that. We basically have the batch dimension, the sequence length dimension, and the hidden, kind of like the embedding dimension. So all of them has to be the same in order for the model to batch them, the system to batch them together. So currently X3 and X4 is with different input dimension. And also for, let's say, X1 and X2, it also cannot work because the cache dimension is different, right? Because the cache has to be reload from the GPU cache. And if they kind of like with a different size, there's kind of like just simply no chance. And then for X1 and 3, they're just doing different computation, right? So, that's kind of like the same story. So to batch multiple requests, right? So we kind of like need to execute, doing the same execution on exactly the same, dimension of the input. So that seems to make things hard. But the solution here is that we can kind of like look into a kind of like a closer or finer granularity that basically, if we kind of like look closer, we will find that the attention is something that kind of like prevent us from batching the computation together. So what we can do here is basically we can just split the computation. So after we get the embedding, after we get the QKV, let's say, we just split the operation. And we're just doing the attention like for each of them, right? So either one by one or trying to find a way to parallelize them or just put them on different GPUs. And then after we kind of like get the attention, then what's the next step of the, of the kind of like the attention network is basically just a fully connected network. Then it doesn't have the cache, right? So also doesn't have the kind of like sequence length. It's just a simple mathematical operation. So there we can just put the things together. It's kind of like we split and we kind of like merge together. And then after we merge, it can be, batchified together. It's basically for different part, we kind of like handle different things in a different way. So that's called the selective batching in the Orca system. So as Shiro mentioned, like we kind of like a system, basically we have tensor model parallelism and pipeline parallelism that's also supported in the Orca system. Well, because even if we are just doing the inference, a model becomes large enough, we still need to split the model weights across GPUs. So this is so the system is implemented based on the like fast transformer, but that's also based on the Megatron system from NVIDIA. And also, since we're just doing the iteration-based scheduling, right? So we don't have to wait until like batch is fully decoded. That basically means we have a kind of like better control of the granularity of the pipeline parallelism. So here, Orca has the better like opportunity to basically, when we are using pipeline parallelism, let's say, we can basically feed the pipeline bubble with kind of like a smarter scheduling. And in experiment, it's kind of like let's say up to kind of like a 300 billion model. I'm sorry, like on a larger like a cluster, it looks like the like Orca achieves much better at the same latency level, achieves much better throughput, basically decoding more like tokens compared to the like FT here is basically just a faster transformer from NVIDIA. All right. Hopefully I'm like giving all the information on time, but like for inference and serving, it's really I'm just giving a quite like kind of like just only a subset of the like work in this area. But this area is really kind of like really active right now. There's a lot of open problems there. There's kind of like more paper if you're interested in looking into them. All of them are coming out actually, if not like roughly speaking last month, it's kind of like within this year. So yes, a very active and an open domain, and I encourage you to look into this area, basically faster and efficient inference and serving of foundation models. So with that, I basically finished my part. This is basically end of the part 1 of our tutorial. And we basically reached to the federated learning part. And I can just hand it over to Sam.
Can you see me and can you hear me?
Yes, Sam, looking good.
All right. Okay, and so you can see the screen that I'm sharing, right?
Yes, that's showing up.
Yes.
All right. Okay, so let me continue with the second part of our tutorial, and thank you all for being here. So before I begin, let me just disclaim that I would like to acknowledge that my presentation only covers a small subset of very vast body of the work in federated learning, and I want to apologize if I have overlooked any significant contributions, and including work of some of the people in the audience due to the limitations of time and scope of this tutorial, and also that the discussion that I will do is very high level. So the outline of the talk is following. So I would first want to cover just the basics of federated learning, mainly its motivation. Then we will look at some particular challenges of federated learning, and next we will look at some proposed solutions that enables deployment of federated learning. All right, so let's start with the motivation. So traditionally in machine learning, we implemented intelligence by collecting all the data in one centralized locations. And over the time, we moved from local solutions to cloud-based solutions, as much of the machine learning success relies on large-scale training infrastructures and the vast amounts of training data stored in one centralized location. But there is a clear downside to this centralized setup, and this is that the data may come from users, and this collection can hurt user experience, which is mostly due to privacy implications. So to protect users' data, the privacy initiatives were already enforced by several government entities. For instance, we have GDPR in Europe or CVPR in the United States. And as such, these regulations, they might or will eventually lead to the limited availability of data. So the question here is what we should really do to actually still use these decentralized data while maintaining users' privacy. And this is where federated learning comes into play. So federated learning is defined as machine learning setup, where we have multiple parties that want to collaborate in order to solve a machine learning problem. And this collaboration is coordinated by a certain server. So the core idea of federated learning is decentralized learning, where the user's data is never actually sent to the server, or even not transferred or exchanged. Instead, what we do is we keep it locally, and we aim to achieve the learning objective using some focus updates from the clients that are intended for immediate aggregation in order such that we avoid privacy leaks. So at least what kind of a basic federated learning idea gives us, it gives us a hope to train a large data set while keeping data private or at least like local. And in addition to that, there is increasing demand to obey data locality paradigm, which means to process data where they were collected. And also there are some recent studies that suggest that federated learning might be actually greener technology when compared to cloud-based training. All right, moving on to the application side. So federated learning has been already used in several commercial applications such as Apple's Hey Siri or QuickType and Google's Hey Google or Gboard, but it's we can still consider it as a relatively new concept, and there is definitely more to come in future. And particularly, this can be very useful in application areas where data privacy is at core, such as medical or banking applications. And here what I list are several startups that are working on these directions. And also, it might be currently the only available solution to ever-increasing demand for of large, high-quality data set to train the large machine learning models. All right, so what I want to cover in the next few slides is I want to just highlight several great resources for federated learning research. In this first slide, I list several open source frameworks for federated learning. This is namely Flower, a friendly federated learning framework. Then there's FedML, which focuses on open and collaborative AI. Both of these are currently also startups created around federated learning. And next three resources are open source software libraries for federated learning, where FLSim, which is out of Meta, and FL Simulation from Microsoft are specifically designed for simulations with PyTorch, while NVIDIA Flare is a domain agnostic and extensible SDK. Also, if you want to kind of keep up with the latest developments in all areas of federated learning, then I would highly recommend you our federated learning one-word seminar that I've been organizing since the start of pandemic in 2019. So we have more than 1,000 participants from all around the world, and then also all talks are available online if you want to watch that. Also, I wish to highlight some of the recent review articles and books that provide deep dive into federated or collaborative learning paradigm. All right, so let's move back to the tutorial content. So we will start with defining different settings in federated learning. So we have two main settings in federated learning. One is cross-silo and cross-device settings. In cross-silo setting, we have a number of companies or organizations that share common objective to train a model based on all of their data, but they cannot share data directly. For instance, this might be hospitals. So here are kind of the main thing what we care about is the privacy. Then in this tutorial, and maybe more kind of related when you hear federated learning, people usually talk about cross-device federated learning, whereby cross-device federated learning, this is a setting where training happens within a server and clients are mobile phones or different IoT devices. We have many such clients, and by many, perhaps you have millions or even hundreds of millions. And each device has a small amount of data, and they want to collaborate in order to train a prediction model or recommendation model of some sort. And once this model is trained, it's also to be deployed or used on those devices. As a next step, we will discuss several challenges that come with federated learning that prevents it essentially from being very easily deployed in practice. So first, as already Chiong mentioned quite a lot, is the communication bottleneck. So here I just highlight the communication bottleneck in just general distributed systems. And as was already told, this is actually way more prevalent for federated learning, because federated learning can be seen as an instance of distributed training. So this communication bottleneck transfers here. But this issue is more prevalent here because we have wireless links and other user internet connections that are way slower than data center links. Secondly, as I said, we have a lot of clients with a limited, and then the aggregated master might have a limited capacity, as federated learning is open collaboration among many, potentially millions of devices. And what we see usually in practice is with the standard kind of setup is actually the cost of communicating updates seems to be a key bottleneck. Just to high level discuss the several possible remedies to this. These are the standard approaches include reducing communication by reducing the size of the communicating updates, and the very popular approach is to give more work to each client by allowing them to run multiple local updates before actually communicate back to the server. And also last one is to potentially do importance client sampling for federated learning. This means that we're trying to find the devices that have the most important updates. And also this is all of these three approaches, they are in a way orthogonal and can be combined for improved overall effect. And we will discuss this more in detail in the next part of the tutorial. All right, then another important challenge to consider is device heterogeneity. As federated learning clients, for instance, you can think here about mobile or different IoT devices, such as smartwatch, can be unreliable and very heterogeneous. So as such, this poses one of the key obstacles for deploying and training in wild, meaning in the presence of very heterogeneous clients. There are several ways to remedy this challenge by designing, for instance, structure resilient algorithms. For instance, this you can achieve by enabling some asynchronous updates. Also, naively, what you can do, you can drop devices that have low capabilities or simply limit the global model size in order to accommodate all the client's constraints. In the next part, we will also discuss more elaborated techniques, how to achieve heterogeneous training. Another important issue related to federated optimization itself is client availability. So the standard in federated learning and cross-device federated learning is that clients are only available when they are on fast internet connection, meaning for instance, Wi-Fi, and when they are connected to the charger. And this standard and a large number of devices in some sense predefine the sampling process, and thus server has unlimited ability to control. On top of that, what we see usually based on these standard criteria, clients will be available to participate in training, typically only during the nighttime, because this is when people are home charging on devices. And this unfortunately could introduce some undesired variations that for instance, optimization algorithms may need to address. And this is still some open questions, because I mean, there are many works on how to handle partial participation, but the usually kind of typical assumption is to assume that we actually have a control of the distribution of a client, which is very unrealistic. All right, so another challenge, which is very much related to the main topic of this tutorial, which is federated learning system. So this is that while on-device inference, so this is the thing that we display on the right, that has been happening for a while, where we only use model for the inference and all the training data are present, and also training are present on the remote server. On-device training is still kind of in a very early stage. And the main bottlenecks here or challenges are that this requires considerably more high precision compute. This would include forward and backward pass, also more, as Chiron was saying, memory for gradient activations, also optimizer states, and also more energy when we compute on devices. And also in practice, to the best of my knowledge, current systems and tools for on-device training are hardly prepared to actually enable that. All right, so this was kind of the set of the challenges that I've discussed so far that was mainly related to the cross-device federated learning, and the next challenges that are more general and applicable to all settings. So first one that we're going to discuss is the fact that clients may have a lot of data, but a very limited labels. And as data labels might be limited, as it might be maybe expensive for clients to label it, or in some application, or it might be like private, or they just lazy. So, and this, what is, I believe, is one of the main reasons why one of the like kind of first applications of federated learning focus on the next word prediction. And for instance, we have Google Gboard, because here you get the, your labels for free. And this brings up a question how to incorporate federated learning, like semi-supervised learning, or how to provide some incentives to your client to actually label their data. In the next challenge, what we do, we discuss the typical modeling issue in federated learning, which is to pick the right objective to optimize. So note here that the not only system perspective, but also client data can be very heterogeneous. And this is not only a challenge, we also see that it's actually a challenge for optimization, but and efficient training, but it also raises a question about whether the utility of one single global model is what is the utility of one single global model to individual users. For instance, the next word prediction that we already discussed. For this is clearly not, as kind of next word prediction pretty much depends on who is the writer. And this led into a lot of interesting directions, for instance, framing federated learning problem as a meta learning problem, or introduction of new personalized objectives, for instance, based on clustering and many other techniques that we will discuss later. Another thing is related to privacy guarantees. While by definition of federated learning, we have that users' data, they do not leave users' devices. But actually what we can't guarantee is that there is actually no privacy leaks in updates or in actually model predictions. And unfortunately, there are actually papers that show that there is a possibility to leak data just by looking at the updates. So, and this is where important techniques such as cryptography, which includes homomorphic encryption or trusted execution environments, or more algorithmic notion of privacy, differential privacy, can be very useful. And we will discuss these later in the tutorial. Next, one of the key features that makes federated learning highly attractive in practice is that it allows training models in collaboration among mutually untrusted clients. So we can actually just gather data from different clients across the world. But the problem is that this makes federated learning a very easy target for a threat known as poisoning, or where we have a small fraction of malicious clients that may corrupt the jointly trained global model, or that have a target to corrupt the model. Therefore, when one design or one deploy federated learning, we also have to think about to employ some defensive mechanisms to avoid these attacks. Another thing that is more like a holistic approach to federated learning is also to discuss like what are the incentives to participate. So for federated learning, when we look at motivation that comes from clients, so this would be local motivation, is we might ask ourselves from the point of the client is what is my motivation to participate? Or even as we discussed before, label the data. Or what is also a local cost, like energy that I need to spend, or actually privacy loss that I'm going to encounter because I'm sharing not direct data, but the updates with respect to my data. Also, do I actually benefit from the federation? What if I train a model on locally? Do I actually get any improvement? Also, when it comes to evaluating your own contribution, it's also hard to say like how much do you contribute to the federation. Also, when it comes to kind of a sharing the income or whatever the benefits comes from model serving, who is the ownership of the model, whether it's a community or global service providers. And this all kind of leads to kind of intersection of these three subjects. One is the statistics, economics, and computer science that already very much kind of interact in a pairwise manner in between each other. But what we kind of see is that through this through this view, when we look at federated learning might be something that sits right in the middle of statistics, economics, and computer science when we model federated collaborative learning as a market. All right, so that brings me into the summary of challenges, where what we saw is that federated learning presents a new realm of unique and complex challenges. And to overcome these issues, we must devise system-aware efficient optimization techniques. And also the key areas to look at is optimization theory and networking and scheduling techniques. And then as a result, we get these techniques to help streamline data processing, improve performance, and enhance the overall effectiveness of federated learning models. All right, so as the next step, we will look at actually like the proposed solution, how to make actually federated learning more practical and deployable. But before that, let me establish some notation. So in general, what we assume that we optimize in federated learning is the following objective, where we have end client, each client has some set of the data. So a loss of each client is denoted to FIX, and then FIX can be further decomposed as the finite loss over the local data points. And we assume that we have access to the stochastic gradient, which might be, let's say, the gradient with respect to single local data points of a given client. And here X is the model parameters that we're trying to find. So the very basic algorithm to solve such problem is what's called federated SGD. So what we have here that each client just computes the stochastic local gradient, returns, then sends it to the server, then server just perform a simple averaging and runs a single gradient step with respect to the average stochastic gradient, which is the estimator of the global gradient. All right, so when we have this established, let's just look at the communication bottleneck and several kind of proposed ideas how to solve this issue. So the main issue, as we discussed, is that in each iteration we have all the workers to communicate potentially dense vector to this orchestrating node. Very naive idea might be we just decrease the size of communicate vector using some lossy compression. And then how the algorithm going to look like? So what we're going to do is we're just going to, instead of communicating full precision updates, we're just going to compress them before communicating, and that way we're going to save some bandwidth when it comes to communication. All right, so how does that look? How does federated learning with compression looks like? So we have a global server that communicates the current model estimate to the client. Each client computes stochastic gradients, but before communicating back, performs the compression and communicate on the compressed model that is then aggregated and it's ready to be sent in the next update, in the next round. So I want to, for this part, I will focus only on compressing the updates, but later on in the tutorial, Hongi will talk also about how to do model compression to actually enable heterogeneous training. All right, so just to give you some notion of what this compression operator might be. So in literature, usually people refer to one popular definition is to consider unbiased compression operator. So here what we require is that this compression operator is unbiased, meaning that when we take the expectation with respect to the compression operator, of the compressed vector, then in expectation we get the true vector, and that we also have the control second moment. And that's control with respect to the norm of the update. So meaning, so what you see here, that as we go to 0, we enforce that essentially the compression error is 0, meaning that compression operator with respect to 0 vector is with probability 1 is the 0 vector. And here, this omega right here is the key quantity. And usually, so here what we do not really have, we do not enforce anything about the compression operator, meaning that it should be cheaper to communicate. But what should be really the case is like this omega, what you would see in theory, that larger the omega, more iteration you have to take in order to converge. But what you want is that essentially this increase in number of communication is in number of steps is overweighted by the savings in communication, meaning that it's actually, if communication is bottleneck, that you have faster convergence in terms of time. Just to give you some examples, here we have, for instance, random sparsification, where we only communicate k coordinates uniformly at random, and in order to be unbiased, we just rescale by the factor d over k, where d is the dimensionality of the model. So this would be the example. So we have here the scaling in order to get unbiasedness, and also we generate the random mask such that here this is sparsification to only 2 non-zero elements. So we have a random mask that essentially has just 2 ones and the rest is just zeros. And this would be the resulting output of the compression operator. Another, apart from sparsification, another popular compression operator is to do quantization, where we essentially decrease the precision. And one way how you can decrease the precision, you can quantize in what we call natural quantization, where you essentially you do element-wise rounding, element-wise unbiased rounding to the closest powers of 2. What is nice about this one, that essentially why it's actually called natural quantization, is because it's compatible with the standard flow 32 representation, where essentially this mapping right here, you don't need to compute anything. You just read everything from the flow 32 representation. So sign stays the same. Then the exponent, which is here, the small out of these 2 values is right here, and then the probability to round up is just Montesa right here. So everything, like, you actually don't need to compute. The only thing that you actually, in order to compute the natural quantization, you just have to sample. But this is independent, so you can do that. You can do this. You can pre-compute in order to speed up compression, in order to kind of not to introduce any computational overhead. And what is nice about this one is that you can show, I mean, easy to see, like if you have flow 32, you actually only only sign an exponent that's only 9 bits, while in the worst case, you would increase number of iterations that's guaranteed by theory by only 12.5%. So this exactly goes back to what I was talking about. If for this one, if the communication is really the bottleneck of the system, then you get guaranteed improvement in terms of convergence time. Another popular compression is Atomo, where we use atomic decomposition of updates with respect to some bases. This might be the standard element-wise basis or singular values or Fourier decomposition. And what we kind of want to achieve is that given communication budget S, you want to communicate the update that has at most, like, only communicate at most as basis elements, but minimizes the variance when compared to the original vector. And this actually can be efficiently solved as displayed here. So essentially, if we have decomposition if this is the actual decomposition with respect to basis, and these are kind of unitary vector or unitary matrices, then essentially you can show if I'm minimizing, if I only can communicate the basis or scale version of the basis, and I have to be unbiased, then the optimal solution is this one right here. So essentially, with probability pi that's defined here, we sample each basis element, and if we pick that, so if this indicator function right here is realized as 1, so here U01 is just a uniform distribution from 0 to 1. So if you essentially with this probability pi, this is 1, otherwise it's 0. If this is actually 1, then we communicate that and we rescale it such that we stay unbiased. All right, so as we saw, it's like the compression might be quite useful techniques when we're dealing with federated learning, but unfortunately, there is one thing: when we have heterogeneous updates and we use compression, what might be quite a bit of an, or might be quite issue that kind of slows down your convergence is that if you wouldn't employ compression and you just run standard Fed SGD, then without any constraint, then at the optimum where X star would be optimum, this guy right here would be 0. But this one on the right, that you would actually end up communicating and the update that you would end up doing at the server might be non-zero if those guys are not all zeros, meaning that actually like you have some kind of heterogeneity. And as such, so in heterogeneous settings, compression unfortunately introduced some extra variance, which prevents the standard existing methods such as FedSGD from fast convergence. So, and the question here is whether we can actually remove this variance. It actually turns out that you can do that. And the idea is quite simple. So instead of compressing this guy right here, what we're going to do, we're going to compress the shift version of that. And if you can make sure that the shift version of that guy converges to the optimal solution, to the gradient at the local function at optimal solution, then you actually recover, like, then you can actually remove the effect of compression. You can remove this bad convergence at the optimum. And this was first noted by Kunster in 2017, also Mishenko at 2019. All right, so now more general version of compression operators is this contractive operators, where we only require that we have that the bound difference is essentially like contractive. Here again, now this alpha that lies in interval 0, 1 is the key quantity. So actually, like smaller we allow it, meaning that like this guy right here is closer to 1, then we actually want more compression. Here again, we don't have any requirements on how expensive is CX to communicate, but by construction, this should be something very cheap to communicate. And if alpha is actually very small, then rather CX be very cheap to communicate, because this will lead to increasing the small alpha will lead, usually you have something like 1 over alpha to be your increase in the number of iterations that you have to take. And also sometimes what you see that in literature, this would be called greedy compressors. And there is also like a nice connection to the unbiased compression operators. You can show that this class is a more general as unbiased compression operators when you scale them by 1 over omega plus 1, where this omega is the thing that appear in the bound in the second moment, is also contrastive contractive operator with alpha being equal to 1 over omega plus y. All right. Some example here, we can have an alternative of random sparsification. Here is a greedy sparsification. So what we're going to do is we're just going to communicate k coordinates with the largest magnitude. As we see here, now we only apply magnitude-based mask, and we only keep the ones that are the largest magnitude. So here, for greedy sparsification to only 2 non-zero coordinates, we would keep 3 and -4. Now, being greedy in heterogeneous settings might not pay off, and there is actually very simple counterexample that essentially shows you that if I want to just naively apply the compression in the same way as we had it for the unbiased compression operators, there we actually can construct very so this is simple quadratic problem, where if I would use just federated gradient descent, I would just get nice, because this is a quadratic problem, I would just get nice linear convergence to the optimal solution. But if I now try to employ compressed gradient, and if I actually here, it's a bit more peculiar, I will start with this point, then what I can actually show is that this greedy compression will pick on the wrong direction locally, that once sum up will be a completely wrong direction, I actually get linear divergence away from the optimal solution. So here the optimal solution would be all zeros, but here you can see that if I take any positive step size, I would just linearly diverge. Now, thankfully, again, as we saw before, there is an easy way, or there were some ways in literature to propose to fix it. One way to do that is error feedback. So how does that work? So essentially, the main idea of error feedback is we just try to correct for the error that we made. So the main difference, what you see here is that when we do compression, we do not only compress the current update, but we also add to that the difference between what we intended to communicate and what we actually managed to communicate. So you see that the UIK is the update that was used by server, but we were originally intended to communicate this way. And this was proposed by Federated in 2014. And there's also a bit more maybe like theory friendly or error feedback that works better in certain scenarios in theory, where what you actually do, it's kind of similar to the shift idea, that you just build this kind of a Markov compressor where you just shift by the previous update, and then you recover that from that outside of the compressor. And the nice thing about that, because this was communicate, like the server needs to know on the average of those. If you do this, you actually don't need to know this guy at the server, because you know, like you were communicate the sum, and that's something that you have available from the prior round. So at the server, you just have to keep the memory of the prior update, and that's it. All right, so that was for the compression. And the second idea that we're going to explore is how to employ local work in order to improve communication to computation ratio. So again, same problem as we had before. And here the idea is to increase computation to communication ratio by giving more works to clients. How can we achieve that? Potentially, very naive idea is to increase mini batch size, but this has some limitations, what was proposed. And it's the most popular approach in practice is to employ multiple local steps or to solve local problems. So one of the workhorse of federated learning, or sometimes people think about this as a synonym to federated learning, is the federated averaging algorithm, where what we do, instead of running a single step, what we're going to do is we receive from the server, we receive the parameter vector xk that's received by all the workers. Now, each worker, what they're going to perform is several steps, meaning this is a parameter of the algorithm. Here is a k steps of local stochastic gradient descent. After k steps, they collect the solution, and that sent, or maybe the difference between the xk and the current new solution is sent to the server. This is equivalent, and then server just perform a simple averaging. What is problem with this one is that essentially in a worst case, because this is purely based on the local information, that one actually cannot show in theory the benefits of local steps due to something called client drift. And therefore, it's essentially, like, you can say that if you go for the worst case analysis, then taking one local step is an optimal, and the local steps all going to hurt you. However, there's also some way that essentially show why federated averaging is in many cases very good in practice. And this is through this new notion of heterogeneity, where Jenny Wang and co-authors proposed the new notion of data heterogeneity that they refer to as an average drift at the optimum. That essentially means like how much the closest solutions to the solution that you converge to, like how much their average is different from the actual solution. And if these two are close enough, then you can show that the federated averaging actually going to work well. So, but this doesn't work when you have when this is actually when the spread is too large, and this is where methods to reduce client drift were proposed. Among them, the most popular is the federated prox method, where essentially what you show, you're trying to solve the local your local problem, but you limit how far you can go actually to the current iterate. Then scaffold that that runs the same local steps as for averaging, but the difference is that they use SVRG-like variance reduction that essentially biases this guy towards the local solutions to remove the client drift. These are while they kind of show a better performance when compared to Fed averaging, these are still kind of not satisfactory as none of their theoretical results they match much of the practical results, and so meaning that they are not actually better in theory than mini batch federated SGD. But still we have actually, but in practice there is a big mismatch between these two, and for instance both of them in practice they outperform mini batch federated SGD by a large margin. So that brings us to more recent work that essentially managed to prove the benefit of local steps. One of them is the proc skip by Konstantin Mishenko and co-authors, where they use this actually quite nice trick where they first reformulate the problem of federated learning into the following problem. So what you can see here is that actually like you allow each client to have their own solution, but then you also enforce the penalty, where the penalty is such that it's 0 if all the solutions are same, infinity otherwise. And what's nice about thing, like here, now you can define this guy to be a function that you can evaluate gradient, and this one is the function you can actually compute the proximity operator. And what the author designed in this work is that they essentially show that if the proximity operator here, the proximity operator, essentially like the optimal solution of this guy corresponds to the simple averaging. So it corresponds to the simple, it corresponds to the communication in federated learning. And what they show is essentially like if you design your algorithm well, you actually don't need to evaluate the prox operator in every single round. And they show essentially that always you can improve upon federated gradient descent. And then another line of work shows that when the data are somehow similar, which is a natural assumption that they are not like arbitrary heterogeneous, then actually local methods benefit from that. And there is a MIME algorithm also, and then there are another algorithm based on the optimal gradient sliding and also catalyst acceleration. All right, so this is for the usefulness of local steps. One thing that we haven't discussed is that those methods that I show you mainly work, or mainly I propose, or that they do show the best results for convex methods. And the reason for that is because federated averaging has coordinate-wise averaging of the weights in each communication round. But when we move to more complex models, such as neural networks, there is a permutation invariance, meaning that I can just, within each layer, I can just perturb the neurons. I do not change the output of the network, but I get many, many different networks. And if I would just average those, I would actually get much worse performance. So this is where work by Hongi and his co-authors comes into play. So this is a federated matched averaging, the FEDMA algorithm, where the authors construct the shared global model in a layer-wise manner by first matching the corresponding neurons. So they first try to find which neurons corresponds to each other. So for instance, like client 1, the third neuron corresponds to client 3, second neuron. So then the output would be average of those two. And then also like enable to, what they do, they also enable model size to increase if you can't find if there are certain neurons that are not present, or that kind of the same function neurons are not present in the other clients. So this is the way how to actually kind of make local methods to work better for larger models such as neural networks. Okay, and the last thing that I mentioned for the for how to cope with communication bottleneck is the important sampling. So here again, the idea is that only workers with important updates communicate to the orchestrating nodes. And then the third question here is that actually which workers should communicate their update. There might be the ones that actually have high local loss, so they didn't solve the problem very well, or maybe they have a large update. Or what we can also do, we can actually try to estimate local updates, and based on that, kind of minimize the variance that was proposed by Ribeiro and Vical in 2020. So this is more kind of relates to more like a standard, like important sampling strategies for machine learning. But when we think about federated learning, there is actually more with this. So when we did kind of construct the important sampling for federated learning, this is quite more challenging in cross-device federated learning. And this is because by construction of federated learning, we actually want clients to be stateless. And also we want to employ secure aggregation. So the master node doesn't really have idea of who are these clients, and that's for like privacy reasons. So what we actually can do in order to enable important sampling is actually this, there is a nice trick that we can actually let clients to figure out themselves whether they have important update or not. So how this kind of looks like in terms of standard federated learning loop. So we have, again, the first two steps are same as before, but now we send some kind of a quantity that represents like how important is the update that is then aggregated by the master, where master sends this quantity back. So this is something that should be very cheap to communicate in order for us to still save the communication. And then based on these quantity, each worker decides whether, okay, is my update important or not? If that's the case, then they communicate, otherwise they do not. So this way kind of save some bandwidth when we don't have all clients communicate back their updates. And this was all to kind of filter important updates cheaply. All right, so this was for the communication bottleneck. So let us now look into issue of the stragglers. So what are stragglers? So when we refer to stragglers, we refer to slow or lagging devices. And as a reason, as the result, they can delay the overall training process due to their slower computational speed, unreliable network connection, or limited availability. So this might overall slow the learning process, or we might have very inefficient resource utilization, or actually the quality of learning. So the model that we converge to might be not as if all the clients do all the work that we require. So in order to cope with that, one can employ asynchronous updates. So in federated learning, this cannot be done directly, because one thing that we want, and one thing that was actually that is embedded in the definition of federated learning, is that each client communicates focus updates that are intended for immediate aggregation. And by aggregation, we mean that they're like average across different clients, such that we kind of like hide in the average. But if we just kind of deploy the asynchronous algorithms very naively, then after each client finishes their communication, the global model should be updated. So in order to kind of extend this, so in order to embed this kind of a secure aggregation notion into the federated learning, there was this paper by John Guillen and co-authors, FedBuff, which introduced one extra layer before actually the model is released to the server, which is that they propose to use these TEEs, so trusted execution environments, that they hold updates until we receive the predefined number of updates here in this example 2. After we receive 2 updates, then the TE performs the averaging, and the average is released to the server that can then update the model, and then release model to the clients that finish their computations. So this way, we can achieve, or we can design asynchronous asynchronous aggregation for the federated learning that respects the fact that we have to actually, like, before the updates are presented to the master node, they are averaged. All right, another problem with potentially heterogeneous clients when it comes to the optimization is, or another proposed solution that was quite, or that is quite popular in practice, is that we will kind of we also allow clients to do a partial work. So we don't want to lose everything that the given client and the client that didn't manage to perform all the computation before the deadline. So what we can do is essentially we can just average whatever update they have at the moment. But what it turns out that in the heterogeneous setting, meaning that it's kind of, if all the clients do not kind of converge to the same optimum, that what happens is that essentially intuitively and or naively, all the clients that or the clients that perform more work, they're essentially going to bias a solution that we converge towards their local solution. And in order to prevent that, we can either essentially like rescale the updates during the aggregation by putting less weight to the clients that did more work, or we can also, or if we can actually account for that, or we know that information that the client is slow before actually the client computes the updates, what we can also do, we can have the faster clients to compute more, but the smaller, more precise updates. All right, so this was about tackling heterogeneity. Also, Hongi will talk more about that in the last part of the tutorial. So next one, what I want to cover briefly is the fairness issue. So here, by fairness in federated learning, this is a fairness when it comes to the performance distribution. So what we mean by fairness is the extent to which the performance of the global model is uniform across the clients. Different metrics that you might employ is either variance, entropy, or a joint fairness index, essentially that are maximized if each client performs the same. And then the choice of index would depend on the data set and your application goal. Some of the federated learning objectives that essentially maximize these or looking at these metrics is agnostic federated learning proposed by Mohri and co-authors, where what we optimize is essentially the performance of the worst performing clients. Because like you can look at this subproblem and that subproblem has the unique solution where we put with one for the client that has the largest loss. And then to make it make more like a parameterized version of this, then Lee and co-authors, they propose Q for federated learning, where they propose the following objective. And what's nice about the objective, that it kind of interpolates between standard federated learning and this agnostic federated learning. So we can show that for Q is equal to 1, this one is essentially equivalent to the objective of standard federated learning, while if you take Q going to infinity, then this guy essentially converges to this guy. All right, and then let me just discuss the personalization. So so what we have are kind of two approaches that we can consider in federated learning. One is like a global only approach, that is a standard federated learning approach, where we learn a single global model that captures all the union of local training data sets. But the issue is that the global model might not work well, for instance, for some minority clients who have very rare data. And such clients, we actually may wish to learn personalized models that are customized to their data set. Then another extreme is the local only approach, where we actually do not do any federation, and each client just computes on their own and obtains a separate model only based on their own local data. This might be an issue when the data sets are too small and we actually do not manage to learn an accurate model that might be quite bad in terms of generalization. So now the question is, what would be kind of the sweet spot in between the local only approach and global only approach. And this is where different personalized objectives comes into play. So for instance, what we can do is we can try to figure out which clients in a federated way, which clients are somewhat similar. This we can do based on some clustering techniques. Also, we can kind of push clients to be similar by having this similarity penalty. So here, if lambda is equal to 0, we get fully local models. If lambda goes to infinity, we get global model. Also, we can do this like this one right here is implicitly. We can do this also explicitly, where you seek the convex combination between local optimal solution and then the solution, and then kind of a global solution that you minimize it. Also, one of the popular approaches is to frame federated learning as the meta learning approach, for instance, here based on MAML, where essentially each client represents one task in a MAML objective. Another popular way to do personalization might be split learning. It's not only for a personalization, essentially also for some kind of a offloading of a computation, where the key idea behind split learning is that we have each client trains a partial deep network up to a specific layer, which is known as the CAD layer. So this is displayed here, but then we communicate all the activations and all the outputs of the layer to the server that essentially finishes the computation and backpropagates all the way here and then communicates back to the client. They have also like a very nice website with all the research that's going on split learning. All right, and there's also one nice recent work that we did with Konstantin Mishenko about personalization. That personalization can actually help optimization itself. And what you can show is that if you actually get over personalization, meaning that each, like you personalize in such way that each client can solve their local problem, so the solution that you find with the personalization is the global solution of the local problem, then you get the kind of the same benefits that you get when you have over parameterization for deep learning. And also a nice thing is that it always exists, meaning that there always exists the split that leads to over personalization. Unfortunately, it's not easy to find such data that would work well in terms of optimization, but also generalization. All right, and the last part that I want to discuss, I think, yeah, we have very limited time, so let me just quickly discuss privacy and robustness. So I'll start with the privacy. So what privacy is, very simple definition might be that it's the ability of an individual to seclude themselves or to withhold information about themselves. Simply say it's a right to be let alone. But the problem with this is like, so when we want to achieve privacy, versus data anonymization is not the safe. And this is the reason versus there is a very well-known Netflix prize that attracted thousands of participants who aim to predict missing entries in a matrix of movie ratings using collaborative filtering. But there was a subsequent work by researchers Narayanian and Swatiko that actually showed that you can identify participants in the Netflix prize training set by just simply linking the movie ratings in the data set with publicly available ratings on IMDb. This is something called linkage attack. Also, they kind of the same problem. We have same problem with federated learning, that data can be in some cases reconstructed from client updates. So how to overcome this? We actually have to provide some formal guarantees of privacy. And this is where differential privacy comes into play. So what is the basic definition of differential privacy is that when we apply our algorithm to the data set, that between D and D prime, they differ just in one client, then the probability that our algorithm gives input S with or without including client that is in D and not in D prime or vice versa doesn't change much, and doesn't change by e to the epsilon, where epsilon is positive. So this would be the ratio, and this is some fixed value that we can't go over. The nice thing about that is, like, if you show that the differential privacy holds, that this is actually resilient to auxiliary knowledge, meaning that DP, so differential privacy, remains effective regardless of any extra information that you might have, or any background knowledge. Also, what is the nice thing about differential privacy, that you get a control over multiple analysis, meaning that you can exactly quantify what's the cumulative privacy loss over multiple analysis of your private data. How this is usually deployed in practice, it's very simple. So you would still use like the same algorithm as you had before. So each client here might be hospital computes their local update. Then what you do, you actually first apply clipping to actually limit the magnitude of update such that then you can apply the noise to kind of hide this update. And then what you're going to do is you apply like independent noise right here, and then you perform a simple averaging such that we can't reconstruct any of the local updates. But because these are independent zero mean noise, then essentially like global update is somehow close to the average, close to the actual average, and you can show that your algorithm still kind of leads to meaningful model. All right, so when it comes to privacy, also robustness is quite important. What we might have, as I discussed before, is Byzantine attacks, where essentially now what we want to optimize is not the objective that includes Byzantines, but only objective with respect to good workers that we denote by G. What we have to have is that the G, the ratio of bad workers is at most 1/2, because if this is not the case, they can actually define their own problem, and we have no way to distinguish which ones are the good ones and not ones. And usually, in order to provide like kind of strong guarantees here, we assume that Byzantines are omniscient. So typical ways how to define defense against Byzantine attacks is to replace the averaging with more robust aggregation rules. Very popular approaches are the middle seekers, where, for instance, like instead of simple averaging, you can find geometric median or coordinates-wise median, or here CRUM estimator, where you do just a average, but you just remove, but you just consider the closest point to the current solution, to the current mean, sorry. Then popular attacks that people usually test against is like the sign flipping attack, label flipping attack, where we flip ground truth labels, also random direction, where you just sample from a unit sphere with diameter p, where the p controls the strength of the attack. Also then more elaborate attacks. One of them is a little is enough attack, proposed by Baruch in 2019. And what you're trying to do is actually trying to limit or trying to kind of concentrate your updates on the boundary of the noise of the good updates. And that's where you're kind of trying to steer your convergence towards some worse kind of quality solution. These are the ones that actually works the best in practice. And also a similar one is the inner product manipulation, where you're actually trying to choose your best updates, your bad updates in such way that the inner product between true mean and the actual output of your robust aggregator is negative. So you're kind of moving the direction that you don't wish to. Some of the recent advances here is it was actually shown that middle seekers are not robust, but thankfully they can be fixed using techniques called bucketing. And also, in order to achieve robustness, you need your underlying optimization to be not permutation invariant. So you have to actually introduce some kind of dependence between runs in order to show that in order to robustify your algorithm, this might be achieved by employing client momentum, or orthogonally, you can also reduce the variance such that the kind of such that the Byzantines don't have they can't actually hide in the noise what we saw before with the Ali attack. And unfortunately, which is maybe very intuitive, is like if you have very heterogeneous data and omniscient Byzantines, then actually like you can't get very precise solutions because Byzantines can exactly hide the noise. All right, with this, I would like to now move it to Hongi, who will finish. And I think we're a bit, apologize that we're a bit over time.
All right, I will share my screen again. Thanks a lot, Sam, for the great presentation. Let's see. Can everybody see my screen?
Yes, I can see it now that you're sharing.
Awesome. Yeah, right. All right, so this will be the last part of this tutorial, basically second like half of the part 2 federated learning part. So I basically cover a few specific topics, basically the backdoor robustness, which is basically a specific type of robustness of federated learning, and also algorithmic approaches for improving both computation and communication efficiency of federated learning, and also some of the on-device federated learning software stacks, and also the federated learning systems. So, all right, let's stop right in. So, as I mentioned, basically, the question to ask here is that, so remember, federated learning is basically trying to leave the private data on device and only communicate the model weights. But I guess one question to ask here is that it's communicating model weights private enough. So it turns out, as I mentioned, there are a lot of papers are trying to show that the model weights can actually still leak some of our private information content in the model. So even if we do not have the data. So basically, this is one type of attack, like a content basically reported in the CCS in 2015. So basically sending the model weights are not enough. Great. So what can we do to basically fix that is that people actually using something basically called secure aggregation in practice. It's combining it's kind of like a natural combination with the federated averaging, right? Instead of just averaging the model weights, we're basically adding some like random noise, but with some specific design. So the design part is basically like this. So say in this particular example, we have 3 clients, but we're grouping them pairwise. Instance that, so the basically client 1, client 2, client 1, client 3, and client 2 and client 3 are grouped together. So within each of the client pair, so they are basically just adding and minusing the like identical noise. So this can be achieved by sharing like same random seeds across different clients. So let's say W1 here minus basically plus the noise, random noise A, and W2 minus random noise A here, and so far and so forth. For basically we have 3 random noises here, like basically ABC. So in the end, what we will find here is basically on the server. So the server doesn't see each individual model updates anymore because by design, we don't want the model basically the global server to see each of the individual model updates because that's not private anymore. However, after we can like still do the averaging, so the noise will be canceled out. So the design here is basically we're adding noise that can be canceled out such that the central server can still see the exact aggregation result. So so this is a way it comes very nicely with a privacy guarantee. However, like when we can like guarantee the like privacy, so the robustness seems to be sacrificed a bit. So it seems like there's a trade-off between privacy and guarantee that since our model cannot see each individual model's updates, so it's easier for if there's a malicious like client or kind of like a worker that's trying to attack some basically hiding some like malicious information in the model updates. It's hard for the global model to check that because it's hard to basically declose anything from the model's information. So there are different ways to basically insert, basically manipulate the model to insert the tag, or basically just managing the data and try to inject that information into the model weights. So here, the attacker is trying to do something that trying to make effective like backdoors. So this is kind of like what's called backdoor attack. It's basically inserting some backdoors into the model weights such that it's hard to be detected and it can persist very long in the global model. So basically the fundamental question here is to basically ask, is the federated learning algorithm robust enough when we try to protect user data privacy as much as possible? So they're kind of like a method like back into 2018 actually. It's trying to develop the backdoor, it's called semantic backdoor. Basically, here is one example. On the CVPR data set, they're trying to find a subset of the data sample. So let's say it's a car with some specific pattern, let's say green cars, and they only inject the tag on those specific pattern. So it's called a semantic backdoor. It's just trying to make sure the model is still correct well, basically classify well on the other type of cars, but only does something very bad on this very specific type of cars. It's called a semantic backdoor. And turns out they can insert the when they are kind of like attack on this specific pattern of cars, so the backdoor can be very effective and persist long enough in the global model. Then basically a year later, the kind of a group of Google researchers and trying to evaluate this backdoor attack on their specific model, basically on their service, and they find is sometimes the attack can work very well. So here is target accuracy. If that becomes high, that basically means the attack is injected successfully in the global model. But there kind of like a validation turns out to say that the attack doesn't seem to be very successful because it does not persist long enough in the global model. So it seems it's kind of like an open problem. So basically there's a kind of like a lack of the final answer. So then kind of like the kind of like a work actually coming of our own group came out and trying to basically adjust that in the more rigorous way, that we're trying to basically prove a theorem that building the connection between like adversary example and the backdoor examples. So it turns out that the backdoor is basically fixing backdoor is as hard as fixing adversary examples. So the later case, basically in the adversary example, is kind of like notoriously hard to fix in the model. So fixing them can be hard. So another theorem like here is basically we can basically detect the backdoor in a model, but turns out that actually requires a lot of like a computing effort. So it's not that there's no easy fix or easy detection unless we pay a good amount of computation. So sometimes if the like backdoor is hidden very well in the model, like basically in the kind of like hiding in the right corner, it's kind of like even harder for the model to basically detect the backdoor. So basically it's, the backdoor can be easy to hide and hard to detect. So what can make it, so in practice, what's the type of, if we are sitting on the defender side, so what's kind of like the attack we should be careful about? So that's something like in this paper is called a tail of distribution attack. It's basically if we imagine there's a data distribution, right? So it's a data distribution about the airplane example. So the common airplane, so that's like images taken from the CVPR data set. So the common type like of airplane we observe every day, it's just something like a normal sample from the CVPR distribution. So there might be something like less common. It's basically, let's say, airplane with a certain type of, certain airplane company. So let's say United Airlines. And the lies on the tail of this distribution, there's something like even rare, like we don't observe, like for every day. So let's say the Southwest Airlines, right? Because Southwest Airlines compared to United Airlines is much smaller. So it's kind of like a much more rare, like we can observe their airplane. So this is sort of like giving like intuition about what's the tail of data distribution may look like. And it can actually happens for both of the image example and the language example, right? So the language example can be the languages that's basically specifically saying some of the certain type of the locations or kind of like a certain people. Right. So and also like let's say for the amnesty example, the tail distribution can be, you know, some of the handwritten digits like written in a kind of like certain flavor. So it turns out that if the attack happening on the like a tail, like, you know, the sample from tail distribution, so it can be very, very powerful. So so here it's basically showing that if the attack is the edge case, so it's basically attack on the tail distribution, it can be quite easy to be injected into the global model, and it can persist very long. But if it's not the tail, you know, the edge case, basically, if it happens on the common pattern of the you know data distribution, then it does not, it cannot persist very long, and it's basically very hard to inject into the global model. So and also like when kind of like a defending, basically try to defend against this kind of like a tail distribution, it looks like it can basically hiding very well and kind of like pass a lot of like this basically defending say the robust aggregation as Sam just mentioned, and also just some norm clipping, which seems to be kind of like effective for defending some type like specific type of attack. So so what's the take home message here? Is basically we have to balance very well on the privacy and the robustness, at least for federated learning. Basically, if we try really hard to protect privacy, we may lose some amount of robustness in federated learning. So a good design of let's say trustworthy federated learning system should basically take both aspects into consideration and basically get a good result. Then let's move forward to talk about the like algorithmic approach for efficient federated learning. So this is kind of like similar to gradient the compression, basically what's happening in the data center when we are trying to communicate the basic gradient into a distributed cluster. The gradient size can be huge because that's the same with the same size with the model. Now as the model becomes really large, then the gradient can also become large. So people basically find something like called gradient compression to reduce the message size we have to communicate across the cluster. So there are several different ways. Basically, one can do the quantization. So basically, we just reduce the number of bits instead of doing the 32 or 64 bits, we just do 2 or 4 or 8 bits. We can just sampling across the dimension. Let's say instead of communicating, let's say GPT model for 175 billion, we can just take sample, let's say 1% or even less than that. So some of the famous example here is basically sparsification. We can just look into the you know the absolute value like of each of the like gradient elements here and try to just communicate the sampled version. And we just take top K of them and just communicate those top K values. And they say the sign SGD, the quantization is basically, sometimes we can even just communicate the sign information, or sometimes we take just the 2 or 4 bits of the quantization. And the people also look into it's kind of like similar to the Atomo method, like Sam just mentioned. It's basically just we can compute the SVD of the gradient, and then just communicate the low rank factorized pieces of those like information. So those for gradient compression. But however, in federated learning case, it's mostly similar to we're just communicating the locally trained model. So this is a kind of like typical procedure of federated averaging. So basically what's actually communicated in the over the network is basically the locally trained model weights. But can we still adopting the like prior Murray designed for gradient compression into model compression? And turns out it's quite possible that it has been studied in this paper, federated learning strategies for improving communication efficiency from Google. It's basically they are trying all the different category of method. So here they try the structure, then the low rank update. So they basically here, so U is actually a random initialized weights that's actually shared across the devices. So it doesn't even need to be like communicated. It can be just generated using the same random seed. And the U weights here is not updated across the local training. So only V weights is updated and also communicated across the cluster. So for each of the round, the V weights are trained on the local devices and are communicated across the cloud, but then just share back across different devices and then just repeat it again. So by this way, like both computation and communication can be saved because you only train part of the factorized model. So that's basically one way. And another way is like basically like random sparsity. So each of the model just adopt like a common mask shared across the class, shared across the clients, and then just only the mask, the kind of like a dense model weights are shared for averaging, and then basically the mask, actually both of the mask and model weights can be trained, and the mask can also be periodically updated to basically attain better final accuracy. So quantization can also be done here. So this is just quite a simple example of a two-level quantization. So the model weights can, each of the weight element can either be quantized into the minimum value of the model elements or the maximum value with a certain probability. So it turns out all of these methods, so let's say the low rank and sparsification and the quantization method, can achieve good performance with respect to either convergence rate or the like basically number of basically accuracy can achieve given certain amount of communication. So other method for low rank training can also be done here is basically so in the previous paper, the U weights are not trained, but people has also tried to evaluate what will happen if both of the U and the V weights are trained. So this, so if we can like train both ways, it seems to be that the computation, the communication efficiency will be worse than we can like freeze one of the model weights, but the convergence can also be, the convergence rate can also be improved. So it's kind of like from the end-to-end perspective, it's really a trade-off between like how much of the local computation we want to put and also the communication versus the final like accuracy. So think about that. It's the same as a good put concept here. Like we want to optimize both of the statistical efficiency, which is a convergence rate, and also the like a system throughput. But this way, for training the low-rank factorization network, we always actually do accuracy drop. And people actually also try to come up with a method to try to mitigate the accuracy drop. It's basically, we can look into the network weights. So this is basically looking into how fast the singular value decays, like among different dimensions of the model. Then we can basically observe that some of the layers tend to appear to have a higher rank, such that approximate them using the low-rank factorization method can just lead to accuracy drop. So in that sense, so one way to go is basically you can just use hybrid architecture, maybe just a switch off some of the layers rank and just factorize some of the layer that's more tolerant to do the low-rank factorization. So in convolution network, those layers seems to be the bottom layer that contains higher redundancy, such that factorizing them will basically remove the redundancy. And it's also safer without suffering kind of like a high accuracy drop. Another like a heuristic turns out to work quite well in practice is basically instead of just as a beginning to start with a low rank network, so people can actually start from the full rank training and then with some like warm up. So this is also appear to be work quite well in gradient sparsification. Basically, we can just use a few epochs of dense training, then becomes gradually making it become sparse. So here we can basically just warm up for each epoch. So like the epoch usually is treated as a hyperparameter during training, then conduct the factorization and find the low rank network, and then train the low rank network until convergence. And appear kind of like all those methods combined together and just put them into practice seems to work quite well, even for the centralized case. So in federated learning case, it can kind of like work better because the communication become really the bottleneck. But even for the centralized training, even for training the GPT model, it can remove like, let's say 40% of model weights and just increase the marginal accuracy drop. So here it's just like loss increase, but kind of like achieve very well end-to-end speed up. So this is the only measure in computation, but when we take into communication, it can be even better. So That's kind of like called the pufferfish method and cuttlefish method published in MLCs. But those methods has also inspired a lot of design in federated learning. So this one is called FedPara, published at ICLR 2022, is that instead of just doing the normal low rank factorization scheme, it's kind of like dividing the low rank factorization scheme even further. It kind of like divides, this work is kind of like divide the rank into a smaller rank pieces. And then the smaller rank pieces, output of the smaller rank pieces is kind of like a merged together using some element-wise hardmark product here. It turns out if basically doing that manipulation of the specific low rank factorization scheme, so the FedPara can achieve like a better compression ratio here. The model ratio basically lower is better. That's the ratio compared to the full rank model training, and can basically better accuracy. So basically the normal rank, this is basically telling us the normal factorization scheme may not be the best way, and like kind of like a more complex factorization scheme can be explored. So that's for the low rank factorization in the normal federated learning scenario. But for as Sam mentioned, like for some of the federated learning scenario is that user may not want to just use the same devices. So user come with different hardware resources. So say some of the people are using the cell phone, and even for the cell phone, different people may have different version. And some people just using smart watch, and some people are using tablet. So different type of devices come with different hardware resources. So the factorizations turns out to be a natural way to basically making the federated learning algorithm resource heterogeneity aware, that such that for a model, basically a device with a larger capacity and the computing resources, it can use higher rank. But for smaller model, it can use lower rank. So the beautiful part here is that on the global server, it can always transform back into the full rank, and then you do the kind of like weight averaging. But the downside is basically when the model is selecting another batch of user devices, it has to factorize again to choose the right rank. So basically, for each of the federated learning rounds, one kind of like one SVD has to be done on the full model. So another another work here is like to avoid the factorization. It's kind of like a field like work actually coming from Sam's great work published at NeurIPS 2021. It's actually try to adopt the order dropout into this to basically tackle the heterogeneity aware federated learning. So in the normal dropout, which basically for each of the layer, the hidden neuron will randomly basically removed from the training. But order dropout is basically have a more specific pattern of the hidden neuron removal. So that's great, like in several sense. So one thing is because the sparsity here is structure sparsity. So it's really hardware friendly. And also it's also kind of like easier for basically model to implement those kind of like dropout scheme. Such that it can easily to match the device basically resources here. So let's say we have a tablet, we have a smartwatch and cell phone. So we can basically detect as a beginning, right? We can basically just detect the profile. Let's say what's the kind of like a model weights, what's the computation complexity and number of parameters, and also our hardware capacity. Then we can just basically group our devices right into different tiers, and then basically slice our model into different of them. So basically have a targeted like a order dropout ratio. And then basically during the training that the order dropout can kind of like take basically participate into the game. So each of the local training can just use an order dropout with a targeted ratio to basically conduct the local training. And then once it's done, it's basically very easy to be merged together into the global model, because kind of like everything is aligned currently. There's no need to basically handle the random mask across the devices. And also this is also beautiful in the sense that because the model training can be done once, but serving is basically has to be done for different type of hardware. So let's say even for new coming hardware here, so we can basically easily slice the model weights to basically just do the serve the kind of like a newly come like hardware with different hardware capacities. And it's also kind of like good for basically dynamic scale for inference. And it's also helped with saving battery life and also kind of like a load balancing. So experimentally, it seems to be that using the field work, it's kind of like a more achieve much better flexibility when serving multiple models compared to just training each individual models individually, and also achieves better scalability here. So with talking about everything in the on-device training, so what actually happens in practice, right? So can federated learning actually run on the mobile or kind of like embedded devices? And turns out that's very possible. There's a kind of like a lot of hardware support and software and hardware support for running actually federated learning on those different type of embedded devices. So here is a Raspberry Pi. It's a quite famous embedded device for different kind of like processing of like local processing or local computation. So it comes with just the CPU core, actually ARM CPU, 4 ARM CPU cores. But however, it can actually, it's as easier, way easier than we might thought about. So we like, it seems that PyTorch has already done quite a good job on coming up with these ARM bindings that can be directly compiled on those like a Raspberry Pi like a board, and you can just run a PyTorch. And the Raspberry Pi also comes with a Raspberry Pi operating system. It's very similar to Ubuntu. So it's actually just running things on Raspberry Pi. It's super easy as we just running something on our own laptop. So it's quite good. With respect to the mobile devices, there are kind of like a different software stack. So TensorFlow itself has a TensorFlow Lite that can basically run on Android devices at least. And this MNN framework is kind of like optimized well on running on different ARM CPUs. So basically it can run on the Android and also iOS, and also basically on the Raspberry Pi system. So all of them basically just using ARM chip. And they seem to be the MNN software stack seems to provide very good support on basically optimizing across those devices. So taking them into the federated learning framework, there's a kind of like this is a paper called the Federated Learning for IoT devices. So basically, on the kind of like on-device training framework, they're just using the PyTorch, or it can also be easily modified to support the other TensorFlow Lite and also the MNN software stack. And to handle the communication, right, we kind of like also need to handle the communication for model averaging and synchronization. So it can, so the Fed IoT framework is built to support the wireless communication using whatever the communication topology, either Bluetooth or kind of like Wi-Fi or MQTT. So MQTT is kind of like a famous and lightweight like wireless communication like a framework to support basically device for IoT devices and easy to basically extend to many different type of newly joined or created like a smartphone or kind of like wearable devices. So so that's basically for like on-device software stack. But what will happen if we kind of like look a little bit the higher layer beyond the on-device software stack is basically the federated learning system. So this paper is published at MLC 2019. This is a very classical design of federated learning system. So so basically for each of the federated rounds, basically the cloud will basically check the available devices here. So maybe some of the devices is not available or they kind of like refuse to join. And then basically for each of the round, the cloud will only sample a subset of the clients. And then there might be some of the client is kind of like has some hardware issue or connecting issue or the battery dies. Then system will basically just ignore their model updates and they use the rest devices to basically just come up with model aggregation. That seems to be a very standard federated like system working schedule. Right. So what happening in on device is basically it's working with this hierarchy. Is basically they have a FL runtime that basically controls what's the algorithm that actually running and all the kind of like machine learning configuration. Let's say the batch size, hyperparameters, and it's trying to talk to the example store, which handles the local data basically with some cryptography method to basically guarantee the data privacy. And also, it's kind of like also connecting with the user app process. So basically, everything's handled by the FL runtime during the training, and this also talks to the FL server, and also it's try to collect the user data and the user app information with the privacy guaranteed, with running on the mobile app. And also for the model developer, at least for the like a system design in Google, they're basically trying to design their model in a separate cycle. And they're basically just need to run some simulation based on some public data set, basically collected from the user behavior and also some internal data set. So once it passes the simulation, it will basically generated based on the simulation, generated the appropriate federated learning plan, and then start to deploy into the server. Then the procedure we described previously happens in the sense that it will basically user start to download the model and try to just contribute their local model updates, and then we start the federated learning session. So that's mostly kind of like give a very high level picture on federated learning. But all of these things basically assume that the model, the model weights are happening in a synchronous way. And then kind of like last year, so Meta basically come up with this system. It's basically looking into the asynchronous way of conducting the federated learning. So because some of the layer, some of the model, let's say, will kind of like return their model weights in a kind of like a struggler, kind of acting as a struggler in the system. It kind of like take much longer than the other devices. It's kind of like a struggler effect talked by Qirong and Sam a lot. So it actually turns out to happen in practice. So basically, that's in the left-hand side. Is what actually Meta observed in their real user case. So if we just do the asynchronous federated learning, right, the server model updates can basically attain much better throughput compared to the synchronized model updates. However, like remember, we always talk about the good put, right? So what about the good put here? Because if we're using the like asynchronous way, we actually have to care about the model updates, the kind of like progress of the model, like how fast it converges. But turns out in practice, if we kind of control well, even in the asynchronous case, the end-to-end speed up. This is basically the end-to-end training loss curve. It's much faster compared to the synchronous case. So it's the good put here is actually optimized with this asynchronous model design. All right, apology again for the kind of like delay of this tutorial, but let me give a quick wrap up here. So the federated learning is basically a promising emerging subfield of federated learning, of machine learning, sorry. So it's just with the design principle that the training should be like only on the data without the basically revealing the user data privacy. And also it should basically enable the user to take control of their data ownership. And also there are kind of like several critical challenges, let's say the trustworthy, efficiency, and also system design, and how to support more devices, and more maybe even like a microcontroller level of the strict device, the resources constraint. So with that, I will basically wrap up here. That's the end of the second part of this tutorial, and probably also the end of the tutorial. Not sure if we will have time for a Q&A session, but yeah, that's all I have to say.
Great. Okay, thank you very much, Hogi. And with that, this concludes our tutorial. Thank you all for being such a great audience and cutting into your lunchtime and all. We as the speakers appreciate it. And again, we apologize for the technical hiccups earlier. So I will be here for a few minutes longer in case, and of course, Hongi and Sam as well, in case you have any questions you'd like to ask us. And for those of you who are going for lunch, please do so with no further delay. Great.
You could offer a video replay after the microphone.
Let's see. So I think that that may depend on whether or not. I don't think CVPR that's really allowed us to record it, unfortunately, but the slides are available online on our website. At least that much we can offer you. Right. Okay. Okay.
Maybe 1 week or 2 weeks late after the meeting.
Oh, no, they're actually available right now. The slides are posted right now. If you go to the virtual site, there'll be a project page and you can click on that to go and see the slides. Okay, cool. Good. Thanks. Right. Unfortunately, it's not recorded. I think CVPR had some issues with that. Okay. Right.
Thank you.
Okay, you're welcome. All right. And okay, I think if no one on the line has any questions, then thank you all. And then so Holly and Sam, I'll catch up with you offline. All right. All right. Cheers.
Right, thanks a lot.
Great. Thanks. And Sam, yeah, you have a good night's rest. I know it's late over there. All right, shutting down the Zoom now. Thank you.
Actually, a question for you.